Good evening, my dear JEE warriors. This is your Captain Shreyas, and you are on the number one JEE English channel, which is Vedantu JEE English. And today we are going to see heat and temperature. Basically, we are going to start off with what are the different temperature scales. Then we will see, you know, the conversion of temperatures. Then we will also go to thermal expansion. Yes, very important topic. Apparent expansion, linear, all these things. And then we are going to go to specific heat capacities and heat capacities, latent heat, which also involves phase changes, and finally calorimetry. Now, these topics are again very important, and I have noted it depending on the weightage which actually comes in the JEE Mains exam. Guarantee minimum 2 to 4 questions can come in your upcoming JEE Mains, right? So let's begin with the class. And if you have forgotten to mark your attendance, do that right now. How do you mark your attendance? Like the video. Second thing, subscribe to the channel because daily content and all super critical, super important. Every single thing on the channel is just for your JEE. This is the channel which is working for all the students who want to learn in pure English, especially from Tamil Nadu, from Andhra, Karnataka, Kerala, Maharashtra, many kids, even in most of the metro cities and Northeast and even in UAE and all, you love to watch the content in English. So that's why we have brought this channel just for you. So let's begin with the class. And I hope I'm audible, visible. Hi Sudarshan, Akhil RX, welcome Zozo, love me, Jaya, good evening. Hi Padmaja. Uh, yes, welcome aboard, welcome aboard, welcome aboard. So let's begin with the lecture. Nucleus, maybe we can take up a separate topic some other time, but not today. Today we'll focus on heat and temperature. Maybe I'll take it up separately. Okay, no worries. I'll be teaching that. Now let's start with the concept of what is heat. Now people get confused when I ask them what is the difference between heat and just energy, right? Because a lot of people think heat and energy are exactly the same thing. Well, it is not. Imagine Shreyas Sir has 100 laddus. Shreyas Sir has 100 laddus. You have no laddu. I have 100 laddus. You have no laddu. I tell somebody, Pandu, come man, give my student sitting over there, give him 20 laddus. Give her 20 laddus. Pandu comes. Pandu takes 20 laddus from me and he is bringing those 20 laddus for you. Imagine the laddu like energy. So I am a body or a system who has 100 laddu of energy. Pandu is some another body, something. Pandu takes 20 laddus, meaning 20 energy units from me, and he's going towards you and giving those 20 laddu of energy. So this laddus which are in transit, which are being transported, that is considered as heat. You cannot say that Shreyas Sir has 100 laddus. So Shreyas Sir's heat is 100 laddu energy. No, wrong. Heat is never in rest. Heat is always in transit. It is in motion. The energy which is possessed by a body, that is called internal energy. So that 100 laddus actually is my internal energy. And when Pandu took away 20 laddus, my internal energy reduced by 20 laddus. It became 80. So those 20 laddus are in transit. That energy in transit is called as heat. Is that clear? Very good. Energy in transit because of temperature difference. This is also very interesting because heat, where does it flow? Why did 20 laddus go to you? Why did 20 laddus not come to me? The answer is I had more temperature, you had less temperature. Heat will always go from higher temperature to lower temperature. Keep that in mind. So if something is hot, something is cold, heat will not go from cold to hot. Heat will always go from hot to cold. Like example, you have water. Water will always go from a high point and it will flow down from the mountains to the ocean, which is at a lower point. As simple as that. Okay, I hope this is absolutely clear. Similarly, thermodynamics or thermo is basically that branch or that part or the unit of physics where we discuss, how temperature, heat, work, volume, pressure, all these things are related to each other. And you will see that heat becomes one of the reasons for the motion and does some work. And James Watt was the person who discovered, heat and work can be interrelated and can be converted. And that was also by accident. Basically, there was a pot on which there was a lid, and he was heating that pot. There was something cooking in it or some boiling water, and there was a stone kept on the lid. As soon as the water started boiling or the food started cooking, there was a lot of pressure which was built up, and suddenly that lid flew off along with that stone. So James Watt thought, oh, there was heat in it, and that heat was able to push the stone. That means it was able to do work. That gave James Watt the idea, I can convert heat into work, and that led to the invention of the steam engines. Yes, so steam was heated basically from boiling water, and steam was sent into chambers which used to push the pistons inside the cylinders, thereby causing motion and thereby running steam engines, power plants, and so many factories. So that was, the invention which led to the industrial revolution also, you can say. Yeah, I hope this is absolutely clear. Hi, Tribhuvan. Opinions, welcome, Aki. All right, great. Hello, Abhinav. Good evening. Good evening. I'm so glad, Akhil, you love the lectures which I conduct. Always there for all of you. Okay, all right. Now, having said that, Having said that, like I said, heat is nothing but the energy in transit. Heat will always go from, hot body to cold body. Now, one very nice example, a mild fire burn makes the skin look red. And what effect does ice have on it? Okay, so basically, understand when you touch some hot object, what is happening? The heat went from the hot object to your skin because it was at a lower temperature. Why do you put ice immediately? Because the heat has gone there. You want to take away the heat. Now your body is at a higher temperature, ice is at a lower temperature. So the heat will come out of your body, thereby reducing the burn or the, you know, uh, wound which is caused on your skin. That's why you use ice. Simple flow of heat. Heat always goes from high temperature to low temperature. High temperature to low temperature. You want to take away that thing. Now there are different ways or in which you can measure temperature. Many times I ask, what do you mean by temperature? And students, because they have by in your board exams in 7th standard or 6th standard, what is temperature? Sorry, temperature is the degree of hotness or coldness which is there inside a body. So if I touch something, I feel hot, high temperature. If I touch something, I feel relatively cold. It is cold temperature, sir. That is what students generally tell me. Is a degree of hotness and coldness of the body. Although, yeah, it is a right definition, nothing wrong in it. But what do you mean by degree of hotness or coldness? I'll come to that. So, my dear students, temperature is basically, yes, it is the degree of hotness or coldness, but you are now studying for JEE, bro. For JEE, I cannot use that terms. So, actually, temperature is a function of the average kinetic energy of the particles in that body. This is the mathematical way of defining temperature. Very, very important. Keep this in mind. Temperature is a linear function. This function is a linear function, by the way. It's a linear function, not a quadratic function. It is a linear function of the average kinetic energy of the particle. So if there are number of particles inside a solid or a liquid or a gas, they are moving, zuk, 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 they are moving. So every particle will have kinetic energy. You measure the average kinetic energy. As you heat it, those particles become more violent. They will start moving. Disco dance. They will start moving. Zuk, 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 even faster. They will get more kinetic energy. Their temperature will go up. So temperature is dependent on the average value of all the particles' kinetic energy. Is that clear? So, this makes things very clear now. If something is hot, the particles inside it are more violent, they are more rigorously moving here and there. Something is cold, they are not so rigorously moving inside that body. So, imagine that all the particles become silent, they go to sleep. They are sleeping means no kinetic energy, they are at rest. Nothing is moving. Pause, statue. They're all like chill, holiday, Sunday today. So, in that case, kinetic energy is zero. Every particle is at rest. What will be the average value? That will be also zero. You can't make the temperature lower than this value because you can't have negative kinetic energy, right? Kinetic energy can reduce, can become zero. Can't go lower than that. So, temperature can reduce, and can't go lower than that. So, can I now say that if the average kinetic energy of all the particles is zero, then it is absolute zero temperature. Absolute zero temperature, which is basically the lowest possible value of temperature. You can't go below it. It's the absolute zero. You can't go below it. Is that making sense? Yes, concept wise, Tribhuvan, I'm going conceptually. You can see that right over here. Hi, good evening, Pritija. Yeah, perfect. Imagine if I ask you, what is the temperature of empty space? Answer it in the chat box. This question can come in your JEE statement base. And you will be confused. What is the temperature of empty space, sir? Oh, sir, the temperature of the sun. Sir, it will be very cold, sir, 0 Kelvin, sir. Sir, very negative temperature. Sir, I don't know. I feel it might be very hot. Sir, I feel it might be cold. What do you think is the temperature of empty space? Somebody is saying 0. I expected it. The answer is option D, none of the above, or none of these, or not defined. Reason simple. The way the way temperature has been defined on the basis of kinetic energy. Remember, in empty space, there are no particles. So, whose average literally are you calculating? Nothing. There is nobody to calculate the average of. So, if there is nobody to measure, what are you measuring? Nothing. So, hence, the temperature of empty space is not defined, is invalid. The question itself is invalid. You cannot say it feels like 0, it is 0, no, it is negative, no. It is not defined because for defining temperature, we need matter, we need particles, we need those particles to be in motion so that I can calculate the average kinetic energy. Without that, I cannot do that. Is that absolutely clear, my dear warriors? Yeah, it will not be negative. But then you might have heard about it that, sir, if you go very high, then the temperature becomes very low, sir. It feels very cold, sir. Yeah, because there are some air molecules, no, here and there. It's not completely matter free. So even if you go in the ionosphere, there are particles. So those particles have very low kinetic energy. That is the reason why you feel very cold. That's it. Simple. Yeah. So unless, yeah, space is not perfectly empty, you can say one or two particles will be there, but that particles get confined to the gravitational masses like the planets and the suns. So, the particles are very close to the planet or that sun or that star or whatever it is. Otherwise, the empty space in between, you will not find particles, or very rare it is. Now, temperature can be measured using a device like a thermometer. There are many more devices like which can measure the temperature, like a thermocouple is there. You have light dependent resistors. Sorry, what am I saying? Temperature dependent resistors. Then you have devices whose you can say conductivity will change based on the temperature. So many devices are there which can measure temperature, but one of the most commonly used devices is the thermometer. It's a very interesting thing. And how a thermometer works is on the basis of something called as the zeroth law of the thermodynamics. Now you'll be like, what the hell is zeroth law of thermodynamics? Zeroth law of thermo. This is so elementary that it was called as the zeroth law, and it came after first and second law. So because first and second law was already popular, so they made this law as the zeroth law, not the third law or fourth law, because it felt very elementary. It says that if body A is in thermal equilibrium with body B, that means temperature of A is equal to temperature of B, and it is also found that there is some other body C, when kept in contact with B, there is no heat flow. So I can conclude temperature of C is temperature of B. When temperatures are equal, they are said to be in thermal equilibrium. Equal, so temperatures are equal, so thermal equilibrium. Then, without conducting any further experiments, one can therefore conclude that body A and body C must be in thermal equilibrium. That means TA must be equal to TC. This is basically the zeroth law of thermodynamics. If a body is in thermal equilibrium with B, another body is also equilibrium with B, then those two bodies are in thermal equilibrium with each other. So a small note which I can mention, that in thermal equilibrium, in thermal equilibrium, in the thermal equilibrium, the temperatures are same, temperatures are same, and no net heat flow happens, and there is no net heat flow which will happen. So heat does not go from here to here nor from here to here. So that is your zeroth law of thermodynamics, and that's exactly what thermometer is based on. You might be wondering how exactly, sir, it is based on the zeroth law of thermodynamics. So let me tell you in a very simple way. There is the bulb of the thermometer. There is the bulb of the thermometer, which is the part which is generally going to touch the human skin to measure the temperature. Now imagine Pandu got fever. Okay, Pandu has got fever. So what are we going to do? We are going to touch the thermometer's bulb to Pandu. So this is our Pandu. This is our Pandu. Pandu is having fever. Pandu is very, very sad. So he is going to put the thermometer under his arm. He is going to put the thermometer under his arm like this to measure the temperature. Now look at it. Inside the thermometer, there is a thermometric fluid, usually the mercury liquid, because it is red in color. It is having good expansion properties. So when you heat it, it expands, and it is visible, and it is in liquid form. So what happens is, if this part is hot, this heat gets transferred to the mercury inside the glass body of the thermometer, and the liquid will expand. And as it expands, there are markings on the thermometer, so you can note down the temperature. If it is a cold body, this heat will be absorbed from the thermometric fluid, which is mercury, and as it cools down, the liquid will contract, and you will see the liquid will come here. You will see lower temperature. So lower temperature, higher temperature. That's how it works. As you can see, the bulb is in equilibrium with Pandu because Pandu is touching the bulb. So temperature of Pandu is equal to temperature of bulb. The bulb is also touching the mercury. So the temperature of the bulb is equal to temperature of mercury. Hence, I can conclude that temperature of Pandu is temperature of mercury. The funny part is, Pandu never touched mercury. Never. Because mercury is, first of all, dangerous liquid to handle. For humans, you should not touch it, not consume it, or definitely. So, what you can see is we have used zeroth law of thermodynamics without you actually touching the mercury fluid. And the best part, which will blow your mind, this thermometer is never actually measuring your direct temperature. It is actually measuring its own temperature. Yeah, believe it. This fluid inside is actually measuring itself. Oh, I am this hot, so I should be this wide. I should be this much. Oh, I am very cold, so I should contract. But it just so happens, because of thermal equilibrium, the temperature of mercury is equal to the temperature of the bulb, and the temperature of the bulb is equal to the temperature of the person there. So, indirectly, it is measuring you. Otherwise, directly, it is measuring itself. How many of you did not know about this fun fact? Yeah. How many of you are mind blown? Yes. Yeah, some amount of heat might be lost, but how much will it be? This is a small thermometer. You are such a big body. You will be some 30, 40 kilos. The mercury weighs how many grams? How much liquid will be there? Yeah. Interesting, isn't it, Abhinav Sudarshan? Sir, in special isolated systems, temperature can be negative. That depends on what you take as the scale. So, when I said the temperature absolutely zero over here, so there are different scales. That's what we are going to come to now. In a certain, like a unit, like you have distance which can be measured in meters or centimeters or like that. Same way, temperature also has different units. In certain units, you start the zero when actually the temperature is lowest. Those type of units are called as absolute scales. What is the meaning of absolute scale? Those scales whose zero actually means that the temperature is really zero, or basically the lowest value. Example, the Kelvin scale. 0 Kelvin actually means it is the lowest temperature. You can't go -1 Kelvin. But there are some scales in which the temperature, when it is 0, does not mean it is the lowest. It is just chosen by one's choice or due to some historical reason. So in that case, it is not an absolute scale. And whenever it is, like for example, centigrade, 0 degree centigrade, definitely not the lowest temperature. You can go even negative. In fact, 0 Kelvin happens to be equal to negative of 273 degrees Celsius. So 0 Celsius feels cold, but you can go colder, -10 degrees Celsius. In Alaska, it can go to -50 degrees Celsius. You can go to -100, -150, -200, -270, -273. But you can't go -274. That is the lower limit of the temperature in Celsius scale. So negative 273 Celsius actually corresponds to the 0 of the Kelvin scale. So coming back now over here to the temperature scales. Yeah. Now remember one thing, that whenever a scale is not absolute like Celsius or even Fahrenheit, what do you think Fahrenheit is? Is it absolute or is it not absolute? Answer it in the chat box. Answer it in the chat box. Yeah. It is not an absolute scale. Perfect. Very good. You will see always the symbol used will be degree. It will be degree Celsius, degree Fahrenheit. You will never write degree Kelvin, because degree is a symbol to signify it is not an absolute scale. But the moment it is an absolute scale, you will just see that pure unit like Kelvin. Okay. Keep that in mind. Okay. Now, the three most popular units which we'll be using, we don't have any other unit in our JEE syllabus. Okay. So, don't break your head over it. Is Kelvin scale, Celsius scale, and Fahrenheit scale. Now, you better remember these values. Yeah, because it is going to be very useful, or else you'll waste time converting, blah, blah, blah. Okay. The most important temperature being 0 Celsius, which is 273 Kelvin, which in Fahrenheit is 32 Fahrenheit. Now, wherever the Britishers ruled, right? So you will see that the temperature scales are in Celsius, but wherever Britishers did not rule, like in America and Australia, I think, or some other places, they use Fahrenheit scale. So you might have heard people saying in the US or in some Hollywood movies that, oh, the temperature has gone to, beyond 100. And you will be scratching your head. What? Beyond 100? That means you're boiling up? No, no, they're talking about 100 Fahrenheit. Okay, so we do not generally use Fahrenheit scales unless you are a medical student where you measure the body temperature in Fahrenheit. Now, that is again historical reason. Anyways, coming back to the point. Now, the boiling temperature where water will boil is 100 degrees Celsius, but in Kelvin, you just add exactly 100. From 0 to 100, Kelvin will be exactly 273 Kelvin plus 100, which is 373. Okay, which is nothing but 373. In Fahrenheit, it is 212. Very easy numbers to remember. From 32, you have gone to 212. So 212 Fahrenheit is 100 degrees Celsius, is also 373 Kelvin. 32 Fahrenheit is 0 Kelvin, which is 273. Is 0 degrees Celsius, which is 273 Kelvin. Similarly, what about room temperature and body temperature? Body temperature is around 37 degrees Celsius. You might have heard if you are at 98 to 99, then you are at normal temperature. But above 99, you slowly start feeling feverish. And above 100, definitely you have fever. So, that is the scale which you use for checking whether you have fever or not in medical sciences. Keep that in mind. Okay. Room temperature is 27 degrees Celsius, which is at 80 Fahrenheit. You don't have to memorize these values, just I'm telling you. Most of the times you will see 27 degrees Celsius and 300 Kelvin used in many thermodynamics problems, right? For room temperature. Lowest temperature is 0 Kelvin, and yes, it is minus 273 degree Celsius. You don't need to remember too many things in Fahrenheit. Just remember 32 and 212, that is more than enough. 32 and 212, that is more than enough. Those values are just given for your understanding purposes. Yeah, Kelvin and Celsius conversions are very, very simple. So, how do we really convert? How do we really convert? Okay, so let me just put it first for Kelvin and Celsius, and then for Fahrenheit and Celsius. For Kelvin and Celsius, the relation is very simple. Whatever you get in Celsius, you add 273 to it, you will get the answer in Kelvin. Forget about these things, but whatever in Celsius, you add 273 to it. For example, you have 27 degrees Celsius, 27 degrees Celsius plus 273. That is going to give me nothing but 300 Kelvin. Simple. Similarly, 0 degrees Celsius plus 273 is going to give me nothing but 273 Kelvin. Similarly, if it is, let's say, 127 degrees Celsius, you add 273 to it. What are you going to get? You are just going to get 400 Kelvin. So, very simple relationship from Celsius to Kelvin or Kelvin to Celsius. Okay. Now, what about Fahrenheit and Celsius? This is something which you need to remember. Either remember this or remember this. I would suggest you can remember this also or this also, because sometimes you might be given the temperature in Fahrenheit and usually you will do calculations in Celsius or Kelvin only. So most likely you are going to use this formula. Now it is easy to remember this also. I'll tell you why. Because if you remember 5 by 9 is F minus 32. See, when Fahrenheit is 32, I just told you about this. When Fahrenheit is 32, that is the freezing point of water, which is also 0 Celsius. Notice how the formula beautifully matches. F is 32. 32 minus 32 is 0. So answer in Celsius is 0. So very easy to remember. Correct? So F minus 32 Fahrenheit, if it is 32, 32 minus 32, 0. 0 Celsius. Yes. And 5F. How do you write the number 5? In alphabets, F-I-V-E. F and 5. So both are together. So if you ever got confused, sir, whether it was 9 by 5 or whether it was 5 by 9, remember that F has that, first alphabet of the spelling of the number 5. So that's how you can easily remember it. So you want to convert, let's say, anything. Say, for example, you want to say, uh, how much is 42 degree Fahrenheit? So 42 degree Fahrenheit, you do minus 32 over here. The whole thing you multiply by 5 and divide by 9. So this will be 5 by 9 into 42 minus 32 is basically 10. So it will be basically 50 by 9 degree Celsius. That's how the conversion happens. Is that absolutely clear? Is that absolutely clear? Yes, very good, very good. Awesome. Very good. Excellente. Awesome, Pratija, Tribhuvan, Abhinav. For getting 150 now. Uh, I think HV, you should be easily be getting 99 percentile if you work hard now for 2 months. 150 is a good score as of now, but not the best score. 150 can be easily taken to 200. Check out my strategy videos which I've done. You will definitely love it and you can improve your scores. Sir, are these the only skills? Can we not use other skills? The answer is no. Definitely there are other skills and you can convert it using a simple logic which I'm going to teach you now. So basically the idea is that all these scales are linear. So for 0 Celsius, if Fahrenheit is 32, for 100 Celsius, Fahrenheit is 212. So this Celsius is how much Fahrenheit? So it is basically a linear scale. So you can use a linear relationship and which you have learned it in mathematics. And what is that relationship that you have learned for comparing linearity in mathematics? If this much is this much, that much is this much, then how much is this much in the other thing? That is basically your 2-point form. As simple as that. It is nothing but your 2-point form. So let me show you what I mean by it. Imagine, imagine, imagine this. This is your x-axis. This is your y-axis. Say for example, there is some freezing point over here, and then there is a boiling point over here. Usually these two things will be given. So let's say x1 degree Celsius is the freezing point and y1 degree, not degree Celsius, some in degree y is the freezing point of liquid or basically water in a particular scale. Imagine x2 is the temperature for the water to boil in the x scale and y2 is the temperature for that same water to boil in some y scale. Then I can directly say, if I now want to measure, if I now want to measure, if I now want to measure in that x scale, if my temperature is some x, how much is that same temperature in the y scale? It is nothing but your 2-point slope form. So what you will do is nothing but y2 minus y1 upon x2 minus x1. Over here, either you can say y minus something, here x minus something, and what is going to come? Y minus y1, x minus x1. This is nothing but your 2-point slope formula. That's all you need to use to convert the temperature. It's that easy. Okay, so you know the temperatures for boiling and freezing in one scale, boiling and freezing in another scale. You want to convert it from one to another. That's all you need to do. We'll demonstrate this with a simple example. Observe carefully. If it is told, example, in a, let's say, Pandu scale, in a Pandu scale, in a Pandu scale, the water, the water freezes, the water freezes at, let's say, minus 40 degree Pandu, and it boils, at, let's say, maybe 160 degree Pandu. Then here is the question. Then here is the question. Then 30, or let's say then 40 degree, or let's say we can take 50 degree also. Then 50 degrees Celsius is how many degree Pandu? 50 degrees Celsius is how many degrees in Pandu scale? That is the question. So let's try and understand this. It's not that difficult. So first of all, we have the Celsius scale and we have the Pandu scale. So Celsius scale, we know the water will freeze at 0 degrees Celsius. We know the water will boil at 100 degrees Celsius. We want to figure out how much is 50 degrees Celsius. So all of this is in your Celsius scale. Now, if you talk about the Pandu scale, here it is. This is your Pandu scale. In Pandu scale, the water is freezing at minus 40 degree Pandu. The water is boiling at 160 degree Pandu. I want to know now, 50 degrees Celsius is how many degree Pandu? I do not know how many Pandu it is, so I'll put that as Y, which I do not know. I want to figure it out. Are you now able to visualize this? Are you now able to visualize this, everyone? Very good. So observe now, how are we going to solve it? All you have to do is use the 2-point form for your straight lines. y2 minus y1 upon x2 minus, y2 minus y1 upon x2 minus x1 is y minus y1 upon x minus x1. That's all. So what is y2 and what is y1? It is nothing but 160 minus y1, which is minus 40, whole thing divided by, this is x2, this is x1. So this will be 100 minus 0 is equal to y minus y1. So y minus 40 upon x minus x1. So it is 50 minus 0. Is that absolutely clear? Okay. So let's see, what do we get over here? 160 minus minus becomes positive. So it will become 200 divided by 100 is equal to y plus 40 divided by 50. 200 by 100 is 2. So that number 50 will come on the top and this will be y plus 40. 2 into 50 is 100. This 40 will go on the other side and y will remain as it is. So y will become 60. So 60 degree Pandu is 50 degree Celsius. Got it, guys? How to do the thermal scale conversion? Is it difficult? No, right? Yes, this is definitely sufficient, man, for JEE mains. What more you need? पांडु क्या है? पांडु पांडु है. पांडु चंपा का दोस्त है. Okay? All right. Great. So let's solve some more questions coming up on your screen, and here it is. Which of the following diagram represents the correct variation between Celsius and Fahrenheit? This was asked in JEE Mains 2025. Come on, not that difficult. You should be able to get it. Nitya, I will see, man, today. Yesterday I could not get any time. I was in office. I just come back. Way they launch, everything was there. So I'll see it today. Okay. Where can you find the test series? Test series is there. Link is there in the description. I think you should be able to see it. Okay. So just check that out. It's there. Ekalavya test series. Hi, Akshay. Okay. Celsius and Fahrenheit. Okay. Those of you who are still confused, think like this. Some critical data points. 32 degree Fahrenheit should be there corresponding to 0 degree Celsius. So when Celsius scale is 0, Fahrenheit should be positive. Here, this is obviously wrong because you can see 0 Celsius is 0 Fahrenheit. This is definitely wrong. Here also, the same problem, 0 Celsius is 0 Fahrenheit. That cannot happen. What about this? When Celsius scale is 0, Fahrenheit is there. When Celsius scale is 0, Fahrenheit is there. So either C or D can be possible. But you have to think which of the two should be the right answer. I'll tell you one simple hint. Okay. When you write Celsius, you say 5 by 9 and you put F minus 32, isn't it? Just open up, you will see 5 by 9 into F minus 32 multiplied by 5 divided by 9, and this is Celsius. Now compare this, guys. Compare this C with the y-axis, Fahrenheit with the x-axis, this 5 by 9 with slope, and this minus with the constant. You can see it is an equation of the straight line with a positive slope. So M is positive and constant is negative. So the graph should be upwards. Celsius versus Fahrenheit should be upwards with a positive slope and a negative intercept. You can clearly see negative intercept and a positive slope. So positive slope is also there and negative intercept is also there. So it should be B option right over here. So D gets eliminated because negative slope and positive intercept cannot be the case. Is that clear how we figured it out? Very good. No, it is not C, it is B. Very good, Abhinav. Lavanya, I hope you understood how we had to solve this question. Very good. Amazing, amazing, amazing. Let's go to the next question coming up on your screen. On the Celsius scale, the temperature of the body changes by 40 Celsius. The change in the temperature in the Fahrenheit scale. Now, this was a tricky question because lot of people made this mistake. Tell me if you are also thinking about the same thing now. Sir, Celsius is there, Fahrenheit is asked. Sir, so Celsius is, you just gave the formula 5 by 9 F minus the 32. So what kids did? Yeah, what kids did? Sir, Celsius is 40. Okay, we'll put 40 over here. Sir, this is 5, sir. This is 9, sir. Sir, this is F minus 32, sir. Sir, we did the math and we got the answer. If you did this and if you found F, this answer is definitely a wrong answer. You'll be like, why, sir? Is the formula wrong? No, the formula is not wrong. How you have used it is wrong because you didn't read the question proper. What is the crux is increased. This word makes a big difference. The change in the temperature is so much. So you need to be very, very careful. Oh, so what to do now, sir? See, Celsius, fine, is 5 by 9 into F minus 32. You just open up the brackets. So it will become 5F by 9 minus 5 multiplied by 32 divided by 9. And this is Celsius. Just think if I took derivatives or differentiated or just took the error part of it, then delta C will be 5 by 9 is just a number, it's a constant, forget about it. Delta F, derivative of a constant is 0. You might be wondering, who are you taking derivative with respect to? It really doesn't matter. Let's say with respect to time or delta t over here. Anyways, it is getting cancelled. Derivative of a constant is 0. Can you see that? So the change is asked. So that's why derivative or difference or error concept is used over here. And now we'll write delta C as a 40, 5 by 9 into delta F. So delta F will be 40 by 5 multiplied by 9. 40 goes by 5 8 times. So 8 into 9. 9 into 8. Guys, yes. Very good. Now you guys have got it. Yes, it is 72 degree Fahrenheit. So hence the correct answer to this is option C, 72 degree Fahrenheit. Is it clear? Everybody with me? Absolutely. Very nice. Very nice. Just 1 second, guys. Okay. So let's go ahead to the next concept of thermal expansion. Now that we understand what are the different temperature scales, how to do the conversion and what is heat. So let's talk about what exactly happens when you supply some heat and as a result temperature changes, and because the temperature changes you will see that the solid, liquid or even the gases, they change their sizes. Now, most of the solids or liquids or gases, when you heat them, they expand. When you cool them, they contract. So the size increases when temperature increases. The size decreases when the temperature decreases. simple relationship. Now, this is a normal behavior. There are some abnormal, every class you have some unique personality. One legend will be there, one sigma, one pro will be there, right? So, anomaly will also be there, where sometimes when you heat it, it instead of expanding, it contracts. Like you might have seen when you heat plastic, instead of expanding, it contracts. Have you tried that? A plastic pen or a plastic mug or something, you heat it, instead of expanding, it becomes shrunk. Even the same thing happens for water between 0 and 4 degrees Celsius. So if you heat water, which is just melted from ice at 0, you might expect it to expand, but actually it does not expand until it reaches 4 degrees Celsius. In fact, 0 degrees Celsius water, after you heat it, it will become smaller at 1 degree Celsius, 2 degrees Celsius even smaller, 3 degrees Celsius even smaller, 4 degrees even smaller. At 5 degrees, again it starts expanding. So until you reach 4 degrees Celsius, it contracts. After 4, 4.01, 4.02, it starts expanding. 5, 6, 7, like that. So, water shows anomalous behavior between 0 and 4. We don't have to go into the details of molecular theory. We just need to study the physics aspect out of it. Okay. Now, this effect has a big role to play in many of the natural phenomena or the application part. Like, for example, our railway track. The railway tracks are made of metal, usually the alloys of some iron. Now, when it is summer, that metal will expand. So, the track which was of this length will probably go this much. And during winter, it will come down. Now, the problem is during the summers. Okay, let's say you made the track that, okay, it is perfectly fitting. It is summer, so it is trying to expand, expand, expand. Imagine there is a track in front of it and a track behind it also. Both will try to push each other during summer. And because there is no space to expand, so what will happen? It will start bending because there is no space, right? It's like a tug of war and it will buckle. So that buckling happens in railway tracks during summer. So that's why what they do, they keep a space in between. Don't expect the railway track to expand by kilometers. It's not like in winter it is 1 kilometer, in summer it is 2 kilometers. No, it is in few millimeters. But that few millimeters makes a matter of life and death only. Because if it doesn't have space, it will start twisting and the train can derail. So what they do is they leave a small gap, and if it expands, in the gap only it will expand and nothing will touch. So that is why that gap is there. Even the same gap is left in our flyovers and bridges. Have you noticed it? Or if you're traveling on a flyover or a bridge, you might have seen some gaps are there. Thuk, thuk, even when you're driving, one thuk, thuk sound will come. You might have wondered why these lines are there. What is this metallic strips? Why are these gaps there? Exactly for that, because even concrete will expand, and if it does not have space to expand, it will crack and it will fall. So that's why we don't, leave it like cut to cut. We need to leave some space. The example of a thermometer, which we just discussed some time back, is also the case of thermal expansion if you realized. Because if you want to measure the temperature, using a thermometer, the liquid inside it should expand. So the heat of the body gets transferred to the bulb, which in turn gets transferred to the liquid mercury, and that liquid mercury absorbs the heat and it expands. If you cool it, it contracts, and that thermal expansion property is exactly what you are using to read how much temperature is there. This also plays a very important role in designing different scales and even volume measuring devices. If you have gone to a bio or a chemistry lab in your school or college, you would have seen, if you take a beaker, it would be mentioned 200 ml, 500 ml, 700 ml, and they write 25 degrees Celsius or 27 degrees Celsius. How many of you have seen that temperature on a beaker or on a test tube? Usually it is given. NEET playlist, PYQ, Muhigan, I think it is there on the NEET English channel. I have done some all the past previous year PYQs on the NEET English channel. You can just check it out. Yeah, it is there. So why the temperature is there? Because imagine you pour some liquid, you are measuring the volume, That might not be correct if it is very hot or very cold. Because when it is hot, even the test tube glass at the end of the day will expand. When it expands, so everything will become big. So the markings will go away from each other. So you are not measuring it correctly. And when it is cold, all the test tubes will contract and it will become small. So the markings will come close by. So actually the volume will not make sense. So that's why they mention the volume, sorry, the temperature, so that when you're performing experiments, you should make sure that the laboratory's temperature is at a specific set value. Got it? Yeah. All right. Radiation, no. Sujit, like I mentioned at the start of the class only, today we are focusing only on these things. We just discussed what is heat, temperature, and temperature scales. Now we are discussing this. Now we are discussing thermal expansion, linear, aerial, and volume. We are coming to that. Okay. So now coming back to the point, this expansion of solids, liquids, or gases can be studied, but the problem is gases behave a slightly different way as compared to liquids and solids. And whenever you want to think about expansion or contraction of gases, we have a separate chapter for that, the thermodynamics and KTG chapter, where you study ideal gas equation. PV is equal to nRT, volume and temperature are related to number of moles and the pressure. So that's how you relate the volumes with the temperature for gases, that to ideal. So we will not focus today on gases. We are going to mainly focus on solids and liquids. Because solid and liquid will not follow PV's and RT. PV's and RT is ideal gas equation. So we cannot use a gas equation for solid or liquid. Correct? Make sense? All right. So separate rules for solids and liquids as compared to the gas part. Okay. All right. Hariharan, it is there, man. Just scroll on the left and right. Just scroll like this. On the app, you will see all the teachers. Okay. And if it is not shown still, just message me or put a comment. I will just see, because today only it was released. Maybe sometimes servers are also busy and things might not be loading. So I don't know. We'll have to check. Okay. All right. No problem. Pranavi, you can check out the classes on the live tab. It's there right over here. If you just go to live tab on the Vedantu JEE English channel, you will be able to see everything. Okay, so these are the upcoming classes. These are the yesterday's classes. Very simple way to check it out. Okay, don't worry. All right, watch the replay. You will understand everything. Now that we are focusing on solids and liquids, we are going to divide our study into three categories. When you heat something, maybe the length of it will change, maybe the area of it will change, maybe the volume which it occupies also might change. So we study these three things, although they are very similar in nature. We'll study these three parameters: length, area, and volume. Linear, aerial, and volumetric separately. The formulas, the idea, concepts are very similar. You will notice. So once you understand linear, easily you will go to aerial and volumetric. So don't break your head. Okay. So we'll study the three different aspects of it. Starting off with linear expansion. Linear expansion means you take a rod, or you take a wire, or you take some object. It has certain length. You heat it. You put it under a flame. You will see it will expand. The length will change by some amount. So the amount by which the length changes depends on how much the temperature has changed, how much was the original length L naught. So it is proportional to the change of the temperature and the original length. So L naught into delta T is the change in the length. Original length was this much. It has changed by delta L because the temperature changed by delta T. Original length was L naught. If the original length only is bigger, the change in its length is also bigger. If the scale or the object was small, its change is also small. That is what this point refers to. Then that constant of proportionality, because it's a proportional symbol, I converted into equality. So I need to put a constant here. That constant is alpha, which is called coefficient of linear expansion. Coefficient, because it's like a constant, it's coming with these two numbers. So coefficient of linear, because we are talking about line or linear measurements. Expansion, because when you heat or cool it, it will either expand or contract. So coefficient of linear expansion. So can I use this formula if the temperature reduces and I absorb the heat? Of course. So instead of flame, you put some ice. This object will contract. And as soon as it starts contracting, there will be a change in length. Yes, delta L will be negative, but do not forget, even delta T will be negative. So if delta T is negative, delta L is negative, meaning length has reduced because you have reduced the temperature. If delta T is positive, delta L is also positive because you have increased the temperature, length will also increase. So this alpha, whether it is expansion or whether it is compression, it is the same. Don't worry about it. So delta L is alpha, L naught, delta T. This is the main formula. Now, if you notice, this delta L actually can be written down as the final length minus the original length. If you take this particular L naught on the other side, then you can rewrite this as L is equal to L naught can be taken common and then 1 plus alpha delta T. So usually this is the formula which you remember. But there is no hard and fast rule. You can also remember this formula, which can be also useful at times. So either this formula or this formula, it is one and the same thing because change in length is final length minus the original length L naught. Is that clear? So this is what it is. Sir, this alpha, sir, who is going to give me alpha? Bro, it is the job of NTA. So if alpha is not given, has NTA made a mistake? No, 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 no. Then they would have given other things like change in length, L naught, delta T, and they will ask you to find alpha. So that's how it is. Just like coefficient of friction. It's a non-theoretical value. It's a practical value, which means you need to perform experiments to get that value, like density, right? Or coefficient of friction. So alpha also is a practical value which has to be done using experiments. Okay. So having said this, what is the unit of alpha? What is the unit of alpha? Unit of alpha is basically Celsius, per Celsius or per Kelvin. Reason is, you can check it out here only. Temperature is Celsius, length meter. This is also meter. Meter will cancel. So this Celsius will come down. So alpha will have the unit of per degree centigrade or per Kelvin. So basically, dimensionally, it is inverse of the temperature. Dimensionally, it is inverse of the temperature because meters and meters have got cancelled on both sides. Meters and meters have got cancelled. Yo, what is this? Meter and meter got cancelled. So this delta T coming over here makes it per Celsius or per Kelvin. The way alpha has been defined also, the ratio to change the length by uh, by the original length per degree centigrade is defined as alpha. So if alpha is lot, meaning if you change the temperature even by a small amount, it is changing its length by a large amount. But if alpha is close to zero, that means even after attempting to rise the temperature by a large amount, there is barely noticeable change in the dimensions. So alpha is less, signifies it does not react to temperature. Alpha is very high, signifies it reacts to temperature and changes its length very easily. Keep that in mind. Okay, everyone? Fine till this point? Okay. Few more things just for your sake. Alpha, if it is positive, it is a normal behavior. It is a normal behavior. But if alpha is negative, it is anomalous behavior. Like water between 0 to 4 degrees Celsius or plastic, when you heat it, it contracts. So if it is a not a normal or abnormal or anomalous behavior, alpha will be negative because when you increase the temperature, the length will decrease, which is not what you would expect usually for a normal solid or a liquid. Keep that in mind. Okay. So this alpha also depends on the material. It depends on the material of solid or liquid as such. All right. So I think it's good time that we start looking at some questions coming up on your screen. What is the percentage change in the length of 1 meter iron rod if its temperature changes by 100 degrees Celsius? Alpha of iron is also given as 2 into 10 to the power minus 5 per degree Celsius. They have given it. Hi Santosh, hi Aditya, hi Sujit, hi Shivansh, hi Pranavi. I'm so glad you guys are understanding everything and focus on the class and keep answering, guys. I would be really happy and proud. Okay, let's have a look. Let's have a look. First of all, change in percentage length is asked. Length original is given, temperature change is also given, alpha is given. So if you notice delta L, I'll just do it on the next slide. I'll get more space. Okay. Delta L is original length into alpha into delta T. Percentage change in length is asked. That means delta L by L naught, if I take, that will be alpha into delta T. So if I want percentage of delta L by L naught, all I have to do is take alpha and delta T and multiply it by 100 so that it is in percentage. So the value of alpha is 2 multiplied by 10 to the power minus 5. Okay, then temperature change is 100 and that 100% 100 will also be there over here. So the power of 10 is 4 over here. 2 zeros and 2 zeros is 4 zeros. Negative 5 will be left with 2 into 10 to the power minus 1, which is 0.2%. So the answer for this question is basically 0.2%. Very fair and simple. Is that clear? Very, very laddu. Very, very simple. Great. Now let's do a killer question. This also came couple of years back in JEE Mains. So this is a very good question. Let's see whether we can understand it. An isosceles triangle is formed using rods of length L1 having expansion coefficient alpha 1 as the base. So there is a rod over here. So basically there is a rod over here whose length is L1 and alpha 1 is the coefficient of expansion. And there are two more rods length L2, which are the two equal sides, you can say, of the equilateral triangle. Okay, sorry, isosceles triangle, my bad. Something like this. This is L1 and this is L2 and this is L2. This base is basically your L1. So that's how the triangle has been made. L2 and L2 are the two equal sides of the isosceles triangle. This is the base whose side length is L1. Okay. Alpha 1 and alpha 2 are given. Now, the values are in such a way that the distance between the apex, which is point A, and the midpoint of the base, that is basically the altitude of the isosceles triangle, remains unchanged. So, they gave the answer only, show that actually it should have been find the value of L1 by L2. Find the value of L1 by L2. So L1 by L2 is equal to basically how much? That is the question. So let's see how do we exactly solve it. Okay, let's assume this answer is not known. This should not have been mentioned. Okay, so let's see how do we exactly do it. First of all, let me think. This is the base. Okay, this is my base and these two are the congruent or the equal sides of length L2. Okay, this side length is equal to this side length having side length of L2. The base has a side length of nothing but of L1. Now let me draw an altitude over here. The altitude will be like this and let's say the altitude value is H. Now let me see that this will be nothing but 90 degrees. And not just that, there is a right angle triangle whose base is L1 by 2 and I'm tempted to use now Pythagoras theorem and you will probably understand why my temptation is towards Pythagoras theorem in a bit. This is hypotenuse, this is the perpendicular and this is also a perpendicular side. So can I then say that if I take L2 square, which is the hypotenuse square, will be H square plus the base, which is nothing but L1 by 2 whole square. Is that right? That is what it would be. Okay. But what do I do now with this? I have an idea. Let me take the derivative of this. What? Yes, I will take the derivative of this. Observe this carefully now. If I take dL2 square by derivative with respect to, let's say, some variable x, d by dx of h square plus 1 by 4 is a constant, d by dx of L1 square. Best part is that h is a constant. It's clearly mentioned the distance between the apex and the midpoint remains unchanged. So h is basically a constant. So the derivative of h or h square should be absolutely 0. Wow, that's one news. Interesting. And how do I take the derivative of L2 square? But not with respect to L2, but with respect to some other variable. You know that you have studied that in derivatives. Yeah, what do? We will take the derivative of L2 square, which would normally be 2 times of L2 into dL2 by dx. dL2 by basically dx. Same logic if I apply over here, I basically use chain rule, guys. L1 square's derivative will be 2 times of L1 into dL1 by dx. This is nothing but the rule of chains. dx 2 just vanished. Let's see what do we get next. We have L1 here, L2 here, dL2 here, dL1 here. I feel like we should rearrange and we have to figure out L1 by L2. So by that logic, I will write it down like this. Take that number 4 on the top. Let dL2 remain as it is. Take the dL1 below, and this L1 will be as it is, and this L2 will be below over here. So therefore, I get this over here as of now. But wait a minute. What do I need? I need to find L1 by L2, and I cannot leave the answer in dL2 and dL1. What do I do now, guys? Think about it. What should I do? What should I do? Yes, everyone. What should I do? Yeah, dL1 and dL2 are nothing but the change in the lengths. And how what is change in the length? Equal to, what is the formula? It is original length into alpha into delta t. Exactly. So this dL2 is the change in the length of the rod 2. That will be the original length into alpha into change in the temperature. Same thing for dL1, which is change in the length of the rod 1, will be rod 1's length into that alpha into the same change in temperature. This will be equal to L1 by L2. Best part is that dt goes. L1 multiplies with L1, L2 also multiplies with L2. So I am left with 4 alpha 2 by alpha 1. L1 into L1 is L1 square. L2 into L2 is L2 square. But I want L1 by L2. So obviously I will be tempted to take the roots on both the sides. That is like this. Therefore, L1 by L2, root of 4 is 2. And this will be alpha 2 by alpha 1. Exactly what I wanted. And that is the correct answer. 2 into root alpha 2 by alpha 1 is the value of L1 by L2. Is that clear? The best part is this problem was not just limited to physics, thermal expansion, but you had to use geometry over here, Pythagoras theorem. We had to also use calculus here, and that understanding can only come when you solve problems. Because you have to think, okay, when I increase the temperature, the length will change by a small amount. So there is a small change in this side length, there is a small change in this side length, and this is not changing. So can I relate this side, and this side? Oh yes, we can relate it by Pythagoras. But if I relate it with Pythagoras, I am not getting change in length formula. How do I get change in length? I can take derivatives. So if I take derivatives, then dl will come. So that dl corresponds to change in length. So that's how I got that idea that I should take the derivatives. And once derivatives come, that's where the physics formula comes. That change in length is original alpha into delta t. Rest all was just solving it. Yeah, I hope this is clear. Everybody with me? Awesomeness. Now let's go to the concept of areal expansion, guys. Ready for it? Areal expansion. Just like when you heat something like a rod, the length changes. If you take a plate, its area will change. How much will that area change? Delta A. That delta A depends on what was my original area. That change in area depends on what was my original area, which is A naught. How much was my change in the temperature, and that constant of proportionality is no longer alpha, rather it is beta. That is called coefficient of areal expansion, because there is an area involved. So just like change in length was alpha L naught delta T, I told you before also that things are very similar. Change in area will be beta into A naught into delta T. A naught is original area, delta T is change in temperature, beta is coefficient of areal expansion. Coefficient of areal expansion. So you take a photograph, a happy family picture, and it's heated. In summer, the family picture becomes big. In winter, the family picture is becoming small. So that's all. So area is changing. Having said that, you can also use the same relationship which you studied in length. Final length is original length 1 plus alpha delta t, but length being replaced by area. Final area is original area 1 plus beta into delta t. That's all. Okay, so keep this in mind. This is very, very similar. If you want, I will make you see both of these equations together. Look at that, these two equations, and then look at this equation. Delta L is alpha L naught delta T. Final length is original length 1 plus alpha delta T. I hope you are seeing a lot of similarity out here. And there is one very interesting thing, that this beta is not independent of alpha, rather it is dependent. In fact, it is 2 times of alpha. Yes, you heard it right. Yeah. I hope you got it. Yes, beta, the coefficient of areal expansion, is 2 times of linear expansion. Think of it this way. Linear means meters, one dimension. Beta means 2 dimensions, meter square kind of thing. So 2 dimensions, so 2 alpha. So 2 times the linear dimension. Okay, so these are some important things which you should definitely know. So let's have a look at some questions coming up on your screen. Consider a sheet of some metal. This is asked in 2025. Length 9 centimeters and width, 4 centimeters. Coefficient of linear expansion is given at room temperature, and mass of the sheet is given. Specific heat capacity is given. Amount of heat supplied is this much. Then the change in the area of the rectangular sheet. Now, I'll give you one formula because that will come later on. But for now, I'll just give it to you. Q is equal to ms delta T. This formula will be needed to solve the problem because change in temperature is not given. See, if you want to find how much is the change of the area, then remember that the change in the area will be the original area into beta into delta T. I don't know the original area, but I think I can find it out. Beta also not given, but I think I can find it out. Delta T is also not given, but I think I can find it out. For that, you need this formula between for the relationship between heat and change in the temperature. Q is ms delta T. We'll be seeing it in a bit once we study calorimeter and heat capacities, but for now, I'm just giving it to you as a takeaway. So let's use that and see what and all is there. Heat is given, which is 8.1 10 to the power 2. So 8.1 multiplied by 10 to the power 2. Is the mass given? Yes, the mass is 0.1 kg. So I'm just going to stick around with that. 0.1. Is the value of S given? Yes, the specific heat capacity is 900. Everything is in SI unit, so I'm really glad about it. So 900. And finally, the change in temperature. Okay, let's see what exactly happens. This will just become 810 is equal to 0.1 makes it 90 into delta T. Therefore, delta T will be 810 divided by 90. 0 cancels. 81 by 9 is 9. So 9 is the change. So 9 Kelvin is the change. Is everybody getting it till this point? Yes? No? Perfecto? Awesome. Awesome. So now what do we do next? Once we know the change in the temperature, what are we going to do? We are going to use it over here. But before using there, one small thing. This area originally will be the length multiplied by the width. So it will be L multiplied by D. This beta is not given, but alpha is given. So it will be 2 into alpha. And lastly, this delta T. So a lot of things are there over here. So let's start substituting it one by one. Okay. First of all, let me put it over here. Delta A will be equal to L. L is 9 centimeters. So 9 into 10 to the power minus 2. D is there, which is 4 centimeters. So 4 into 10 to the power minus 2 into 2 into alpha. Where is alpha? Alpha is here. So 3.1 decimals and 10 to the power minus 5 into change in the temperature, which is 9 over here. That's it. So that will give me the change in area. Is that clear, everyone? How do we do it? Thank you, Kovar. All right. That gives me the answer as 2 into 10 to the power negative 6. You can just do the calculation. It's not that difficult. So 2 multiplied by 10 to the power minus 6 is the answer. Yeah, meter square. Everything is SI units. So 2 into 10 to the power minus 6. Okay, very good. Perfect. Yeah. Hi, Praveen. When it is not parallel means Mr. Pianist. All right. Everybody clear? Shall we go ahead to the next concept? All right. Areal expansion is done. Now it's time for volume. If you have understood linear and if you have understood area, you can easily even predict the formulas for volume. It is not even going to take 2 brain cells to figure out what the formula will be. Change in length was original length alpha delta T. Change in area was original area into beta delta T. Change in volume will be original volume into, instead of alpha, beta, then gamma. That's it. Gamma into delta T. That's it. Simple. Okay. So after alpha comes beta, after beta comes gamma. Simple. And the final volume, just like final length will be L naught 1 plus alpha delta T. Final area will be original area 1 plus beta delta T. Final volume will be original volume 1 plus gamma delta T. Very predictable. Okay, also known as the cubic expansion or the coefficient of volume expansion. Coefficient of volume expansion or coefficient of cubic expansion, whatever you want to say. Okay. Sir, is gamma related? Sir, is gamma related to alpha or beta? Yes. Just like beta, which was 2 dimensions because it is area. So it was double of alpha. It's obvious volume is 3 dimensions. Alpha, alpha, alpha. Alpha plus alpha plus alpha is 3 alpha. So gamma is 3 times of alpha. So gamma is basically 3 times of alpha. As simple as that. Okay, clear about this? Very good. Now there was a very interesting question which I had seen, which was on gas, and they had asked to find, gamma. Like for example, for a gas, volume is given as some constant into T cube. Can you find gamma, coefficient of volume expansion for that thing? They had asked this kind of question. People started scratching their head. What the heck is this question? Volume of a gas is some constant into T cube. Find gamma? Yo, what is this? How do we do it? So then, if you think about it for a minute, then you will understand gamma is related to change in volume, change in temperature. But change in volume, change in temperature, how do I do? Then people understood change. I have to take a big change, I can take a small change also. If I want to take a small change, then better take derivatives. Derivatives are always easier to look at if you have such simple equations. So how about this? You take volume, you take K, and there is T cube. How about this? Taking derivative on both the sides. So derivative with respect to anything you can take. Derivative of T cube with respect to, I don't know, some random variable I have taken, guys. T, X, anything you can take, doesn't really matter. Okay, so K is a constant, that's why I put it out. You take the chain rule, so dt cube by dt and dt by dt. Okay, so what happens now? Observe carefully. This is dv by dt. Oh, by the way, I had used chain rule over here, as you can see, because I can't differentiate capital T with respect to small t. All right. So derivative of t cube is 3t square. dt by dt, just leave it to itself because anyways, Pavam fellow is going to get cut. dt from both sides. But that was the whole point of this thing. Now I've got dv is equal to k 3t square into dt. Now I have an idea. Change in volume is actually speaking, just observe this carefully, guys. If I just had to write simple change in volume, what would I write? Original volume into gamma into change in temperature. That's what I would write by the definition of volume expansion. Yeah, coefficient of volume expansion, how are they related? I have just mentioned it over here. Change in volume is gamma, original volume into change in temperature. But these temperature changes are very small, so that's why dt. Change in volume is also very small. K is there, 3 and t square is there, multiplied by dt is also there. Best part, bro, dt and dt just got cancelled. Yeah, what am I left with? This gamma, all right, volume is there. Okay, I'll just put it over here. So volume is there, my gamma is there, is equal to, we have 3 kt square. So sir, I got the value of gamma, it is 3 kt square by v. Wait a minute, there is more simplification you can do. Can't you see volume is kt cube? Can't you see volume actually is nothing but, volume actually is nothing but k into t cube. So just put kt cube over here. Wow. So once you do that, more things are cancelling. T square, and here also t square, here k, and here also k. So what am I left with over here? I am left with t multiplied by gamma is just equal to the number 3. So therefore, my gamma value is 3 by t. That's it. Done and dusted. Yes, Kaushik, whatever you have doubt, please ask. But did you love this question? How gamma for a gas can be found using derivatives and ideal gas equations if needed. Okay, but here nothing was needed as such because volume and temperature were anyways directly related and given to me. Okay, so once volume temperature relationships are known, you can differentiate such an equation. You have to use chain rule, then you have to use the definition of volume expansion, and then resubstitute back the original equation, and then you get the value of gamma. Very lovely, amazing, super duper problem. Yeah, loving it. Very good, guys. Now, let me tell you, if you have a gas or a liquid or a solid who expands, who changes its volume when you heat it, it's obvious that the density will go down when you heat it. So, you might need sometimes density calculations. Now, density is mass by volume. Volume is there in the denominator, and things in the denominator do not look so good, right? So after using some binomial approximations and all of that, there is a simplified formula, which you better remember, Okay. See guys, it so happens that if you want to figure out the new density of the solid, because when it is not heated so much, the molecules are close by, but when you heat it, the molecules go far away, so the density will change, mass per unit volume. If you take here one volume, here one volume, the mass is less here, so the density will decrease. So to find that density, the formula is original density upon 1 plus gamma delta T. but usually gamma values are very, very small. You just saw it, like 10 to the power -5, -6, -7. So when you take this on the top, you can actually use binomial approximation. Yes, you can use binomial approximation. Like for example, if I have 1 upon 1 plus gamma delta t, I can easily write it as 1 plus gamma delta t, the whole thing raised to -1. And binomial approximation says that if you have 1 plus x being a very small number raised to some real number over here, then you can approximately say that it is 1 plus that power, which is n, into that small number x. So we can then say this is nothing but approximately 1 plus that number will come over here into gamma delta t, which approximately makes it 1 minus gamma delta t. So anything like this in the denominator, which is difficult to calculate, I can just shift it in the numerator side using the binomial approximation formula. So that is the reason why you just saw that these people down here just went up very beautifully, making the formula look very easy to calculate also. So the final density will be original density into 1 minus, be careful, minus gamma delta t. So usually our volumes are, original volume 1 plus gamma delta t. Final area is original area 1 plus beta delta t. Final length is original length 1 plus alpha delta t. Density is original density 1 minus, not plus, minus gamma delta t. That is the biggest catch over here. Okay, fit it inside your head and do not make this mistake. Is that clear, everybody? Yeah, that plus and minus sign, and why that minus sign came because of binomial. I have explained it to you over here, that minus. Okay. So for example, they can give you a question something like this, that maybe some liquid has a density of 2000 kg per meter cube at room temperature at 37 degrees Celsius. Find the new density. Find the new density. That is the question in front of you. Let's see how do we exactly solve it. We have to find the new density. Okay, we have to find the new density. New density will be old density into 1 minus gamma delta t. Oh, so sorry, I did not give the value of gamma. Yeah, the value of gamma is given to me as 0.1 into 10 to the power minus 5. 0.1 into 10 to the power minus 5. So let's start substituting everything. Original density is 2000. 1 minus gamma is given to be 0.1 into 10 to the power -5. Change in temperature. Think about it. Room temperature means 27 degrees Celsius, and 27 degrees Celsius, to take it to 37 degrees Celsius, the change in the temperature is just 10. So just have to multiply it with the number 10. So this will become 2000 into 1 minus, this is 10 to the power -6. Actually, this 10 will cancel. This will just become 10 to the power -5, I believe. So this will become 2000 into point. Think of it like this. 10 to the power -5 means 0.1234 zeros, and then you have 1. So what will this number be? 2000 multiplied by 0. Think about it. What will this be? 0.99999. Yes, that many nines, guys. That many nines. 0.99999. Exactly. Everybody got it? Yes or no? Quickly let me know in the chat box. Yeah? Very good, very good. Come on. But yes, Lavanya is saying, sir, approximately, sir, it is 2000 only. No, sir. Sir, approximately it is 2000 only. That is the problem. That only is the problem, my dear. You cannot say approximately 2000. Then what's the fun in the problem? Because I know it will be 2000 only, almost, but options will be in decimals. So you need to be careful about it. First of all, swallow these three zeros. So it will become 2 multiplied by 1, 2, 3. So 999.99. So 2 into 999.99 will be how much? 999.99. You multiply it 2 times. How much will you get, guys? Close to 1999. But two decimal places I will move up. Yeah. So it will be 1999.98. Just check it out. So this kg per meter cube, that accuracy will be needed, expected in your numeric questions. Don't say 2000. Even if you see an option saying 2000, don't mark it. If it is a objective type, if it's numeric type, so you have to go till this decimal. And if it is options also, just see till second decimal you have to give it correct, or else you will get negative -1. Yes, be careful. Got it, everyone? How this has to be solved? Very nice. Now let's go to the next question. This was asked during COVID era. Oh, what is it? It says non-isotropic solid is there and non-isotropic. What is this? Hold on. The coefficient of linear expansion is this along x, this along y, and this along z. Then the coefficient of volume expansion is how much? Oh, along y, z, and x is given alpha, and they're asking what is gamma. But why all these things alpha? I thought alpha was same. Maybe there is some catch in the question. Now the catch in the question is this word, non-isotropic solid. What is the meaning of it? See, isotropic means direction does not matter. The properties, the behavior is the same whether you go along x, y, or z. Now, most of the solids are or liquids are isotropic. So in such cases, the alpha in the x direction, alpha in the y direction, and alpha in the z direction will be same, and it is just alpha for a isotropic solid. Isotropic. So directions, all the directions or all the dimensions are the same. No matter which dimension you go, the properties, the behavior is the same. So a non-isotropic will have different alpha in x, y, and z, which is precisely the case. Okay. We know that gamma was 3 alpha for a normal regular solid liquid gas, meaning isotropic solid. Now, sir, you did not teach non-isotropic solid. That is what many kids told in the mains exam. That's what JEE is exactly testing. Are you using your presence of mind? It's not there in NCERT. It is not there in many JEE books also. After that COVID era, people started adding that thing in the notes. Before that, JEE will always set an example. Suddenly, they will put a bouncer question. You cannot say this is bonus. You have to use presence of mind. Presence of mind has to be used like this. Gamma is 3 alpha. 3 dimensions are there, x, y, z. So maybe it was alpha plus alpha plus alpha. It just happened to be that alpha was same everywhere. So it became 3 alpha. So if I have a non-isotropic solid, alphas are different. Alpha x, alpha y, and alpha z are different usually. Different. So my gamma won't be 3 alpha because alpha is not the same. Rather, it will be alpha x plus alpha y plus alpha z. Oh, that's it. Then it is nothing. You just have to add some numbers. It's like a second standard problem where you have to add number 2 plus 3 is 5, like that. So nothing great in that. So first number which we have to add is 5 into 10 to the power negative 5. The second number and the third number coincidentally are the same. Now be careful. Lot of people say, sir, this is also 5, this is also 5. Even I felt the same initially. But look at the power. This is minus 5. This is minus 6. So be careful. So 5 into 10 to the power minus 6 plus 5 into 10 to the power minus 6. Oh my God. Okay. So let's do one thing. 5 into 10 to the power minus 5. 5 plus 5 is 10. So this will become 10 into 10 to the power minus 6. 10 into 10 to the power minus 6 is nothing but 10 to the power minus 5. 10 to the power minus 5 is common. So 5 plus 1 into 10 to the power minus 5. 5 plus 1 is 6. So 6 into 10 to the power minus 5 per degree centigrade. That is your gamma. That's it. So that is your gamma. Okay. So they had asked what is the value of C. So in this case, it will be nothing but if you write it in the form of 10 to the power minus 6, it will be 60 multiplied by 10 to the power minus 6. So the value of C is 60. That's how that numeric question was. Isn't it interesting question? Very interesting. So be prepared. That's what I'm saying. When you have to solve questions, don't be limited by what you are learning in the textbook or the lecture. Use your common sense because that is what you will need in the real life. Because your real life is not based on textbook knowledge, and that is what JEE, IIT, NITs stand for. Why do companies, why do people pay so much to recruit IITians, BITSians, NITians, triple ITians? Why? Because they do not just, they know that they have passed an exam and they do not just do rote learning. They are applying their presence of mind, common sense, out of the box thinking, analytical skills, visualization skills. All these things are important. So this is one such kind of problem. Yeah. Hi, Salomi. Good evening. I'm doing very good, Abhinav. Yeah. Oh, I think Abhinav is asking, how are you typing in such font? Even I am interested now how Salomi did that. Maybe you are typing it in some word or something and then copy pasting it here. Okay. Now, last point over here is the concept of apparent expansion. Like I was talking about some time back, that if you pour some liquid in some container, then when you heat it, the container will also expand and the liquid inside it will also expand. So earlier, if the container marking was some ml, after heating, if it shows some new ml, if you measure that difference, that won't be the actual change in volume. That is a pseudo change, not so real. That is apparent change, what you feel, what you are seeing. It is apparent, but it is not real. So the apparent expansion happens because the liquid is also expanding and at the same time the container is also expanding. So whatever apparent expansion you get is original volume, whatever you measured. Let's say at a standard temperature you are measuring, okay, this many ml, 50 ml. Okay, so that 50 ml will come here into change in temperature. Maybe you are heating it and maybe you change it by 15 degrees centigrade. So 15 will come over here. Then instead of gamma, here you will have the difference of the gamma of the liquid inside and the container. Yes, the difference of the liquid gamma and container's gamma. That difference is called the new apparent gamma, apparent coefficient of expansion. So that will give me the change in the volume. That will give me the apparent change in the volume, which is noticed, For example's sake, let me just show you. Okay, one second. I'll just show it to you here. Then we'll go back to that slide. Say for for some liquid measured in a beaker at calibrated temperature, liquid measured in a beaker at calibrated temperature is, example, 50 ml. If the temperature is raised by 20 degrees Celsius, find the apparent change and the new volume of the liquid. Given to me is gamma of the liquid is 3 multiplied by 10 to the power minus 5, or let's say we'll take it minus 4. Gamma of the container is 1 into 10 to the power minus 4. Okay, this is what is given to me. So let's see how do we do this. First of all, we have to figure out what is the apparent change. And this is a problem of apparent expansion because container and the liquid will expand differently. So the apparent change will be original volume into gamma apparent multiplied by delta T. So what is that original volume? Original volume is the true volume which is at the calibrated temperature. Meaning, I know that actually at this temperature I should get the true reading. So that is the original volume. So I'll just put 50 in milliliters. Gamma apparent is the difference of these two numbers. So 3 into 10 to the power minus 4 minus 1 into 10 to the power minus 4. Difference of the temperature is nothing but 20. Okay, so this will become 50 multiplied by 3 minus 1 is 2. So 2 into 10 to the power minus 4 into 20. Okay, 5 twos are 10. This 0 is also there. So 1 0, 1 0, and 5 twos are 10, one more 0. So 3 zeros are there. So 2 into 10 to the power minus 4 will be multiplied by 3 zeros of that. And this will become 2 into 10 to the power minus 1, which makes it nothing but how many ml, guys? 0.2 ml. So the change in the volume apparently, and this is all apparent, is 0.2 ml. This is what you are going to see the apparent change. But if the question says also figure out actually what is the new volume, then what will you do, guys? Then what will you do, guys? The actual volume of that liquid will be the original volume of that liquid into gamma of the liquid into delta T. The original volume of that liquid was 50 ml, gamma of the liquid was 3, delta T is 20. So 0, 0, 5 twos are 10, 3 zeros. So 3 into 10 to the power minus 4 into 3 zeros. So that will make it 3 into 10 to the power minus 1, which is 0.3 ml is the change in the volume, of that liquid. So the new volume of that liquid will be, don't take apparent change, take the actual real change. So it will be the old volume 50 ml plus 0.3 ml. So that will be 50.3 ml. I have seen many kids adding 0.2 ml to 50 ml, which is absolutely incorrect. Yeah, don't do that, because that is apparent change, that is not the real change. The real change in the volume of the liquid is 0.3 ml, guys. So 0.3 ml has to be added to the original volume to get the actual new volume of the liquid. But if you are performing the experiment inside the beaker, then you will feel that the volume has only changed by 0.2 ml, which is actually incorrect. So that is what this calculation is for. Okay, hi Karthik. Yes, your Cap 2 is here. I hope you guys are understanding these questions. Okay, very interesting and amazing questions. Now it's time for starting heat capacities. I hope you guys are ready. Yeah, everybody with me on this? Awesome. So let's start with it. Let's take a 5-minute break quickly. Okay, I'm just going to take a 5-minute short break before we start the class for the heat capacities phase changes, calorimeter concept. It's not going to take a lot of time. Just take a 5 minute break, okay? And we'll return. Yo, I'm back. Welcome, welcome back. Yeah, hi Akshay. Yeah, I know time is completed. Hi Shrinav. Hi Mahesh Kumar. Bhavin, Karthik, PVM. Good evening. Yes, yes, yes. Good evening. Hi Karthik. Hi Lavanya. Abhinav, welcome back. Yeah. Sir, put Sui in class means? What do you mean by put Sui in class? What is this Sui, man? Hi Mahesh. What is Sui, bro? Sir, how long will the session? This will go on for more 1 hour, not max more than that. Yeah. Okay, great. Yeah, right, Padmaja. All right, let's begin. Let's begin. CR7, what the hell? Cristiano Ronaldo. Yo, Ronaldo I have to put. Why should I put Ronaldo in the class? What is he going to do? He's going to kick the ball, no? I mean, that's all, right? Ronaldo is going to kick the ball. For that you want. Why? Which ball is there over here to kick? No ball are there. Yeah, chill, bro. I'm not sure why you want Ronaldo in this heat class. There is water, there is no ball. Yeah. Ronaldo can only kick balls. That's it. He can't teach heat. Okay. He can't kick this beaker. Okay. All right. So, talking about the next concept where we will be discussing how much heat is needed or if heat is given, how temperature changes happen in a solid, liquid, or basically a gas. So, how heat and the changes in temperature are related, number one. Number two, we are going to talk about if I want to freeze something, or if I want to melt something, or if I want to vaporize something, or if I want to condense something, then what amount of heat is required? Basically, phase change. Now, there are three phases. Basically, if you know, solid, liquid, and gas. You would have studied this in your high school only, no? Three states of matter. How nice science was or subjects were, 4, 5, 6 years back. Or I think just barely 4, 5 years back, that's it. And suddenly, now you are in 12th standard and you are thinking, oh my God, I used to study such simple things. And suddenly, what am I all studying? Derivatives, integration, matrices, determinants, differential equations, inorganic chemistry. Insane. But yeah, three states of matter, solid, liquid, and gas, right? Now, basically, we are not just talking about ice, water, and steam, but in general, anything. Maybe if you take iron, if you melt it, it will become liquid, molten iron. If you heat it more, it will vaporize into steam, but that will be at very, very high temperature. Or if you take oxygen gas, if you cool it, it will become liquid oxygen. And if you cool it further, it will become solid structure of oxygen. Now, usually you find things in either their natural solid, gas, or liquid form. But yeah, this phase transformation can definitely happen. Yeah. Uh, Thank you for registering for JEE in 2025. This is very serious, Albert. If you have got such a notification, maybe you can send me a screenshot on Telegram, Captain Shreyas, and we'll try to see what can be done. And if many other kids have got that kind of a thing, just put up that comment after this video ends, or even in the registration video, 7 documents. Other kids also might see that, and maybe they will reply to that comment. Okay. Plus, send it to me on my Telegram. I'll just have a look into it. Maybe somebody else has got that. Okay. Now, coming back over here, when you move from solid to liquid, liquid to gas, you always have to supply the energy in the form of heat. Yeah, you have to heat it in order to change the state. In the reverse way, you have to absorb from the system or take it out from the system in order to take it from gas to liquid and liquid to solid. That's one simple rule which you should know. Okay. Solid heated converts to liquid. Liquid heated converts to gas. Gas being cooled converts to liquid. Liquid being cooled converts into solid. Now, that is one thing. Whenever the ice or the solid converts into liquid, that happens at a very specific temperature called as the melting point. And the reverse also, when the liquid solidifies into the solid, it happens at a very specific temperature called as the freezing point or the melting point, one and the same thing. So this basically happens, okay, yeah, either at the melting point, you can say, or at the freezing point. Same thing, liquid going into gas, which is vaporization, or the reverse, this gas converting into liquid, which is condensation, happens at the boiling point, which is also a very unique temperature for a material. For water or H2O, we know freezing point is 0 degrees Celsius and boiling point is 100 degrees Celsius. But for other solids and liquids, it could be different, and it is different. We know that. Okay. Now, remember one thing. Until the last bit of ice converts into water, the entire temperature remains the same. Yeah, if it is 0, it will stay 0 until the last bit of ice converts into water of 0 degrees Celsius. And once all the ice has melted and converted into water, which will be at 0 Celsius, after that, if you heat it, continue heating rather, then that 0 Celsius water will go to 1 degree Celsius. Then that 1 Celsius water will go to 2 Celsius and 3 and 4 and 10, like that. It will keep changing the temperature. The same is also true if you freeze the water. When you keep the water in the fridge, slowly the temperature will come down from 20 to 10 to 5 to 1 to 0. After 0, the temperature will not change because slowly the water is turning into ice. Until the last bit of water converts into ice, the temperature remains at the freezing point for water, which is 0 Celsius. Once all the water transforms into the solid ice, then if you further continue cooling it, then 0 will become -1 Celsius, then -2 Celsius, -4 Celsius, -10, -20, like that. It will keep on continuing on the negative side. Is this clear? This means whenever I convert solid to liquid, liquid to solid, or same thing also true for liquid to gas and even gas to liquid, the temperature remains the same in the phase transformation. Three phases are there. Phase being transformed, the phase transformation, the temperature remains the same, meaning it's a isothermal process. Iso means same, thermal temperature. So same temperature is maintained throughout that process of the conversion. Once that conversion is over, that's it. Temperature starts changing. Like when you take water, which was just melted, it slowly increases temperature 1 degree, 2 degree, 5 degree, 20 degree, 80 degree, 90, 99, 100 it will reach. After 100, it will not increase the temperature. Slowly the water will convert it into steam until the last bit of water is converted into steam. And once that water is converted into steam completely, all that steam will be now at which temperature? 100 degrees Celsius. From 100, if you continue heating it, it will go to 101, 102, 105, and so on and so forth. So that's how the temperature changes happen. Temperatures never change when the phase transforms, but once the transformation is complete, either solid, liquid, or gas, then the temperature changes depending on how much heat has been supplied. How many of you understood this concept till here? Give me a thumbs up. Yeah? Sir, where can I put quotes for the topics? Sir wishes, sir. Yes, as clear as water. Quotes for the topics as in AI, the way the AI you mean? Oh, and see, guys, I'm so lost into teaching and working that I forgot only today. Yeah, I mean, I remembered, but in the class, I was fully engrossed into teaching. Bro, man, it is your day today. Yes, kids. What is it? All the Pandus and Jampas, it is your day. It is Children's Day. Very, very happy Children's Day, guys. Yeah. A very, 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 very happy Children's Day. Amazing. All the kids out here, thank you so much for loving, supporting, and we will continue giving you so many surprises every single year. Shreyas Sir comes up with some surprise. Vedantu comes up with a surprise for all of you. Like today, we gave your best friend buddy over here, which is Ved. Okay, so all the best in using Ved, and all the best for your future too. Thank you so much, guys, for loving us. Okay, means a lot. A very, very happy Children's Day once again. All right, so understood this very clearly. Okay, now this heat which is needed to convert from solid to liquid, or liquid to gas, or gas to liquid, and liquid to solid, that heat depends on two things. Number one, how much mass is being converted, M. Second thing, what is being converted? Meaning, is it solid, liquid, or gas, or is it water? Is it carbon dioxide? Is it metal? Is it some plastic? Is it some blah, 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 whatever material? So it depends on two things. One is amount being converted. Second is what is being converted. Okay, which material, which compound, which element is being converted. So that heat formula is given by M into L. M for mass, L for latent heat in that transformation process, latent heat of that phase change. Remember, the temperature is constant whenever the phase transformation happens. Very, very important. Temperature does not change, isothermal process. And that Q is M into L. Q is M into L, whether it is vaporization or condensation at boiling point, or it is liquefaction or solidification at melting point. It's the same formula, M into L, but L will change. For example, if you talk about ice converting into water, then per kg, or rather I would say per gram of ice, you will need 80 calories, or for a kg, you will need 80 kilocalories of heat to convert from ice to water or water to ice. But for water to steam, or from steam to water, you will need 540 calories for every gram, or 540 kilocalories per kilogram, because kilo will cancel. So you can see that. So for every gram of ice to be converted into water, you will need 80 calories of heat to be supplied. And if you want to convert that water into ice, you will need to suck out 80 calories of heat per gram. Same way, if you have 1 gram of water which has to be boiled into steam, you will need to supply 540 calories of heat. And the reverse, if you have 1 gram of steam and you want to condense it, liquefy it into water, you will have to absorb 540 calories of heat. Okay. Now, you might be also wondering at this point of time, how much is a calorie? Well, 1 calorie is nothing but 4.2 joules. On the exact form, 4.18 joules. This conversion is also called as the mechanical equivalent of heat. Sometime back, I was talking about James Watt discovering the steam engine by accident when the lid of a pot blew away when he heated it. So heat usually was measured in calories. Long time back I'm talking about. Okay, some few hundred, well, little bit more than 100 years back. So heat was measured in calories. Work, the concept of work was measured in joules. People took heat separate, work separate. James Watt told work can be converted into heat, heat can be converted into work. Then they thought, if heat and work are actually two physical quantities which can be interconverted, we know apples and oranges and apples, if they have to be, transferred, you need the same kind of units conversion, or basically they will have same dimension. So that's why that conversion factor was found, and it was found that a calorie is nothing but 4.18 joules. A calorie is nothing but 4.18 joules. Is that clear? Very good. I'm so glad, Jawar, you love our classes, love my classes, and just seeing my video, bringing back the old, oh, Jawar, you are J 2025 student and you got 99 percentile. Amazing, amazing, amazing. That's too good. And I'm really proud of you, Jawar. And so glad to see kids just like you. And especially you came on Children's Day. That is even more, I would say fulfilling for and satisfying for me. And kids like you always come back to the Vedantu J English channel. They always comment also. And I have seen many comments and students, juniors liking those comments. And many seniors guiding that I watched this video and I got this percentile. I'm in this NIT, this IIT. So I'm really proud about this. I'm so glad. Yeah. Rani, I know little bit of Tamil. I was born in Tamil Nadu, but I can't speak Tamil very fluently. Or but yeah, I know few things, yeah, here and there. All right, let's go back. Now, you might be also wondering, sir, what is this 1 calorie exactly definition? How do I know what is 1 calorie? So that also has a definition. If you take 1 gram of water, how much grams of water? Water, normal water, 1 gram. This is very small, 1 milliliter basically, ml. At 14.5 degrees Celsius, and you heat it till it goes to 15.5 degrees Celsius at your normal atmospheric pressure of 1 atm. How much ever heat you give, that is exactly a calorie. So a calorie unit of heat was defined as the amount of heat required to take the temperature of 1 gram of water at your normal pressure of 1 atm from 14.5 Celsius to 15.5 Celsius. That's it. That is how a calorie is defined. How is a joule defined? We know 1 joule of work is when you take 1 Newton of force and displace it by a meter. So 1 Newton meter is 1 joule. We know that. Yeah. I hope this is clear. All right. High and low temperature bores condensate made of which material? Oh my God. See, I always expect these kind of questions. Sir, black hole, what is there inside black hole? Sir, what is this rocket ka? Sir, in that material, that solid state is there. Okay. Yeah, a lot of things to study, bro. But if I had a lot of time, I would have answered every single question. Yes, maybe in the long term batches, when we have a lot of time, I will sit and discuss every single thing with you. Einstein's relativity to, black hole theory of Stephen Hawking, radiation from black holes, or plasma material, plasma TV, how TV works, everything I will tell you if, we have a lot of time and we are sitting 1-to-1 or maybe in a long term match. But, JEE 2026, 2 months, plasma is not going to come. Sorry, I'm little selfish now because for me, my students' marks are very important. When I have time, I happily discuss everything. Okay, cool. And anyways, having said that, there are also some solids which do not convert into liquids before converting into gas, like the naphthalene balls. Naphthalene is a special compound, organic compound. You might have probably studied it in organic chemistry, right? That naphthalene is used to keep away pests and bugs. So naphthalene does not convert into liquid. If you have seen those white color balls, you might have seen it in the house near the kitchen or in the bathroom. Yeah, or sometimes they are colored in the toilets, in the urinals. They keep yellow, orange, pink, all weird colors. You see some smell also. Even many times they keep it in the toilet so that fragrances will come. So that solid is converting into a gas directly. That is sublimation. Okay, otherwise you have melting and then you have vaporization, but you skip the melting and vaporization and directly convert to gas. That is sublimation. As simple as that. Okay, so all these things done. All right, M into L formula also I told you. All these things are done. Now, if I show you specifically how the temperature changes as you heat a solid, convert it into liquid, and finally take it to gas, this is how it looks like. Observe. Maybe the ice was at a very cold temperature. Maybe it was in Kashmir. Maybe it was in Alaska. Maybe it was in Antarctica at minus 25 degrees Celsius. It can be minus 30 also, minus 50 also, minus 10 also. Slowly you heat the ice. From minus 25, it will go to minus 20, minus 20 to minus 10, minus 5, minus 1, and then 0. 0 is the melting point. So for some time, you can see the temperature is not changing. Why is it not changing? Because it has to melt completely. Until that time, temperature won't change. It's an isothermal process, any phase change process. Once all that ice melts into liquid, then 0 Celsius will become 1, 2, 3, 4, 10, 9, 100. Till 100, temperature will change. What is 100? What is special about it? Yes, it's a boiling point. So until every bit of water will convert into vapor, the temperature will remain the same. And then after you get the steam, that steam's temperature will keep on increasing. 101, 102, 103, like that it will keep on increasing. Is that clear? Pandus, Champas, everyone? Very good. Hi Harita, awesome. Akshay, looks like your question is answered. Great. Now that you understand, okay, this is how the curve is going to look like. By the way, this curve came in JEE means how does that graph look like? And based on the graph also there were some questions. Okay, we'll do that. You might be wondering, sir, this graph, sometimes it is less steep, sometimes it is more steep. Is that steepness related to something? The answer is yes. The steepness of the graph, except for phase change, it is flat, slope is 0, but other places there is some steepness. So what is that steepness, somehow related by? So let me tell you that slope is related to something called as specific heat capacity. So we'll understand this concept of specific heat. Now, once a phase is changed, let's say it is in a liquid form, until it goes into the boiling phase, the temperature will change. So whatever heat you give will be converting into thermal energy, increasing or changing the temperature. So that amount of heat supplied is related to the temperature and how much mass you are heating. By this formula, heat supplied or absorbed is the mass being heated or being cooled into change in temperature, whatever it is, into a constant of that matter, which is different for water, which is different for alcohol, which is different for carbon dioxide, which is different for iron, which is different for mercury, which is different for every single element and compound. That constant S is called specific heat capacity. What is it called? Specific heat capacity. Now, this formula is typically used for solids and gases. For solids, oh sorry, why did I say gas? My bad, solids and liquids. My bad. Solids and liquids. Ayo, sir. Why, sir, will you use this formula for solids and liquids only? I'll tell you in a bit. So if I know how much mass is there, if I know how much S is there, I know delta T, I can easily find the heat required. Okay, fair enough. So, sir, can you tell me some specific example of this? Why not? Let me tell you. See, guys, for example, for water, right? For water, specific heat capacity is 1 calorie, that's how calorie is defined, per gram per degree Celsius. So if 4 grams of water is taken from is taken from 20 degrees Celsius to, let's say, 35 degrees Celsius, how much heat would you require? Let's say I'm taking a simple laddu question so that I can explain you the concept. We know we know that heat is nothing but m into s into delta T. What is the mass? I have taken 4 grams of water. What is the specific heat capacity? It is 1. What is the change in temperature? It is 35 final minus initial, which is 20. Just do this. So what am I going to get? 4 multiplied by 15. 15 fours are 60. So 60 calories. Everything was in calories. So 60 calories of heat will be required to take the temperature of 4 grams of water from 20 to 35. Is that laddu simple? Okay. Yes, sir. Understood. Now, this is okay as long as I said it is solids and liquids. But the moment you have a gas, you do not use the exact same formula. So for gases, you generally don't measure the amount in kgs. The amount is measured in basically moles, and moles is measured in N. And over there, you don't have specific heat capacity. You don't have specific heat capacity. What, sir? You don't have specific heat capacity? Then what term do you have? You have molar specific heat capacity, which symbol is C, small c. So the formula looks like this. Instead of mass, you have N. Instead of S, you have C. And temperature change, that is as it is, no change over there. So instead of MS delta T, you have NC delta T. NC delta T. And the unit of C is also very important. The unit of C is how many calories you give per mole per degree centigrade. So instead of calories per kg, it becomes calories per mole. That's the big difference out there. Is that clear? Yeah, you study this C in thermodynamics. Now, the interesting part is that this value of C depends on how you are heating it. Yes. Imagine you are taking that gas, you have put it in a chamber, and the chamber is rigid. So you are not allowing it to change the volume. In that case, it is CV for basically isochoric process. And the value of CV, we all know about it. It is nothing but R upon gamma minus 1. Gamma is the ratio of specific heat capacity, which depends on diatomic, monatomic, triatomic, degrees of freedom, and all of that. I hope you remember that. If the pressure is maintained, you allow it to expand, but pressure is the same, then it is a isobaric process. In case of isobaric process, it is gamma R upon gamma minus 1. And in fact, if you subtract these two, very, very important, guys, I think we have discussed this number of times, Cp minus Cv, that is R, which is also called as the Mayer's relationship. The difference of Cp and Cv, Cp is always more than Cv for a gas by a value of R, that is Mayer's relationship. And if you take the ratio of it, Cp divided by Cv, that exactly is gamma, adiabatic ratio or specific heat capacity ratio for constant pressure and constant volume. But it just doesn't end there. If you find the value of, let's say, Ca, which is adiabatic process, for adiabatic process, what is the value of specific heat capacity? For adiabatic process, Q is 0. So no matter what the temperature changes, Q should be 0. So C must be 0 because LHS is 0. So RHS is 0. And specific heat capacity for constant temperature, which is isothermal process, that comes out to be infinity. That comes out to be infinity because if you take delta T below Q for isothermal process, temperature change is 0. So any finite number by 0 is actually indeterminate. But if you take the limit of it, where delta T tends to 0, then the limit of this argument will become infinity. So specific heat capacity becomes infinity. These are very specific things which you should know, can come in match the following also. And many books will not cover it, and many teachers will also not cover it. So I'm covering it over here, and that is the speciality of the Vedantu JEE English channel. Or else you are following some random one shots here and there, missing 100 of things, you will miss out on the marks. Yeah, very good. Now you might be wondering, sir, you have CV, CP, CA, CT, such nice, beautiful things for, gases. Don't you have such beautiful things for solids and liquids? Papa, they are. Nothing they have. In fact, if you measure SP, specific heat capacity, for a solid or liquid at constant pressure, and specific heat capacity for constant volume for a solid or a liquid, they are roughly the same. Yeah, they are not different. They are roughly the same. So basically, SP is almost equal to SV. Yes, SP is slightly more, but that minute difference is negligible. Always SP will be, any specific heat at constant pressure should be more than specific heat at constant volume for all the normal solids and liquids. So for solids and liquids, there is no much of difference. So it is almost equal. This is also something which can come in your JEE mains, maybe as a statement based, or maybe in JEE Advanced, or maybe in IIT or UGEE exam. Who knows? Okay. So all these things are, very important, small, minute details also I'm trying to cover over here. All right. Now that we have understood what is specific heat capacity, what is latent heat, okay, there is one more thing which we need to learn, and that is basically your heat capacity. Heat capacity is simply mass into specific heat capacity. That's it. So our usual formula had heat is mass into S into delta T. You just write both of them into one single term. So either you put capital S or you put capital C, whatever you want to call S delta T. So that is basically called heat capacity. Now usually many books will use capital C. So if you want, I can use that same symbol to maintain that consistency. But do not confuse this capital C with that small c, which is molar specific heat capacity. You don't confuse with that. Okay. So this is your normal regular heat capacity, which is just mass into specific heat capacity. So going back to that example of water, which we had just solved, if somebody had asked, what is the heat capacity of water? In this case, well, the heat capacity of water, if somebody had asked me, the heat capacity, I would say it is M into S. What is M? Mass is 4. What is specific heat capacity? 1. So the answer will be just 4. But please keep in mind, it is just calories per degree centigrade. There is no per mass or per mole is not there. It is just heat per degree centigrade. That is the unit of heat capacity. Mass into specific heat. Very few questions will be there on heat capacity directly, but it's a term which you should be familiar with. Now, if I go back to this diagram and if I ask you, okay, listen, this is temperature and let's say this is heat. I'm heating it. What is this slope really, you know, meaning? What does it really signify? Then I will think like this. Probably it's there on the next slide. Okay. So if you look at the slope of temperature versus whatever heat which is supplied. Now the heat supplied will also be dependent on the time. So if I wait for more time, more heat will be supplied. So even though if it is a temperature versus time axis, please remember my heat which I supply will be proportional to the time that I wait as I'm supplying that particular heat. Okay. Now the slope of this particular graph will be nothing but the temperature change divided by the time interval. Now, the time interval, as I said, is directly proportional to the heat. So, delta T will be some constant, I will put it as K, into basically the heat. Okay, K into heat. But wait a minute, I know the formula for heat. Heat is nothing but M into S into basically delta T. Delta T cancels. So I am left with 1 by Km and 1 by S over here. So basically the slope is inversely proportional to S. If the specific heat capacity is more, the slope is less. If specific heat capacity is less, the steepness is higher. As you can see from here, slope is inversely, it is there in the denominator. So that's how the slope will change. Is it absolutely clear? This kind of question has come graphically in the exam. Okay. So there were graphs with more and less slopes or comparison based. So these kind of things are very, very important. Very good. Amazing. Amazing. Now, having said this, one more concept, how aquatic animals are staying inside Antarctica. I will explain if you want to. Who is it? NIT, IIT and Madras. Don't worry. I will explain if you want to. Not a big deal for me to explain. I can explain it to you. But before going ahead, sometimes the question can be, you know, find the water equivalent of a metal of 5 grams with specific heat capacity of that metal is, let's say, 4 calories per gram per degree centigrade. Find the water equivalent. Now you might start wondering what the hell is water equivalent. Let me explain this to you. Basically, imagine you take water and you take the metal. Now, how much metal you have? In this case, you have basically 5 grams of that particular metal. Okay, you have 5 grams of that metal. Now, imagine I have water on the other side. You have water. How much water? I do not know. I'm just saying M. You give both of them same amount of heat. Same amount of heat. There should be same change in temperature. So that mass of the water which absorbs the same heat for the same temperature change as that of the object or the other material, that mass is called the water equivalent. So this M that you see over here, this M is exactly the water equivalent. So the water equivalent is always the mass of the water which behaves like the solid or liquid when heated by the same amount for the same change in temperature. So basically heat is same, temperature change is same. So what could be different then? Well, if you compare Q over here versus Q over here, Q will be nothing but mass of the metal into specific heat capacity of the metal and multiplied by delta T. This should be exactly equal to, because heats are the same, here also delta T will be there. Here you will have mass of the water, which is M, into specific heat capacity of water into delta T. As you can easily see, this delta T and delta T has just cancelled off. So over here, mass of the metal is 5 grams, specific heat capacity is 4, is equal to mass of the water, I do not know. Specific heat capacity of water is 1 calorie per gram per Celsius. That's a standard thing. So therefore, my M will be 20. 5 fours are 20 grams. Always the answer will be in grams. That means this 5 grams of the metal will behave exactly like 20 grams of water. So the water equivalent of the metal is basically 20 grams. Is that absolutely clear? Everybody with me? Okay. Perfect. Understood? Yes. No. Perfecto. Great. Great. Somebody was asking, sir, how does fish survive in Antarctica, sir? Please explain. Okay. I'll explain this to you. Very simple. It is not that difficult. See, if you draw the graph of density versus temperature for water specifically, then that graph looks something like this. Very, very important graph. Observe it carefully. And this graph peaks at 4 degrees Celsius. That is the most important thing. And at 0 degrees Celsius, it is over here. This is the density. Now the anomalous behavior happens here. Anomalous behavior happens here, this part, because usually what should have happened is when you increase the temperature, the density should decrease. So this is basically your normal behavior. The anomalous behavior happens right over here, where density increases when you heat it, which should not really happen. That is water for you. So because of this, what happens, I'll tell you. Look at it in different stages. Okay. Imagine this is the sea floor or the river floor. Okay. And imagine this is the water surface. Below this, our nice water is there. Okay. This water is there. Outside, the temperature is very, very low. Some negative temperature. Okay. Very, very cold. Negative temperature. Very cold it is. And this water might be at some temperature. I don't know. Some random temperature. Okay. Right now, the density is same. Now, see what happens. Because outside it is very cold, water might be now warm because outside temperature has become cold suddenly. So, the water will start becoming colder. Now, normally, when the water becomes cold, the temperature reduces. The lower temperature water will be denser. The lower temperature water will be denser. Which surface will get cold first? Obviously, the topmost surface, because what will happen is the heat will flow. Heat will flow out of this. So, as a result, what you will notice is the surface which is exposed to the water that will cool, and once it cools, the density increases. So you will see it will be more dense as compared to the water below over here. So you will probably see something like this. This will be more dense. So I'm shading it slightly more. Maybe this is uh, let's say 5 degrees Celsius water, and here this is 6 degrees Celsius water. 5 degrees Celsius water will be denser as compared to 6 degrees Celsius. What happens because the density is more? That dense water will come down. It will basically sink. Now that 6 degrees Celsius will go up. So eventually what will happen is, now observe that 6 degrees Celsius water will become 5 degrees Celsius, and that process will continue. Eventually, imagine the uppermost layer soon will then become maybe 4 degrees Celsius water. The water below is at 5 degrees Celsius. That water will again sink below. The heavier water will sink below. Lower temperature means higher density. This is all normal behavior. The problem happens once the entire liquid is now back to 4 degrees Celsius. Below this, all the problem starts. Now, let's say all the water is at 4 degrees Celsius. It all started from example 6 degrees Celsius. So the water became cold, that water sank, and that circulation started. And finally, the water became 4 degrees Celsius. That water will also sink, that 5 will become 4, and all that water is now at 4 degrees Celsius. Now imagine the outside exposed water surface, okay, is very, very cold. Outside it is very cold. So what will happen? That 4 will become 3. But that is the funny part now. The funny part is the moment that exposed part, because it loses heat, becomes 3 degrees Celsius, it will not become dense, rather it will become light as compared to the other water. So that is the interesting part. So this will become 3 degrees Celsius, but this will still remain 4 degrees Celsius. 3 degrees Celsius water is less dense than 4 degrees Celsius. Is that clear? And that less dense liquid stays there. So that 3 will become 2, 2 will become 1, 1 will become 0. Oh, wow. So what is happening, sir? What is happening, sir? Basically, the water below is now trapped at 4 degrees Celsius. And this water above is exposed to the cold environment, and it will just keep cooling, and it can't sink because it is lighter. And once it reaches 0 degrees Celsius, obviously it is going to freeze. obviously it is going to freeze and you will see something like this. Eventually, you will see a layer of ice over here. You will see a layer of basically what? Ice over here. And what is there below? You will see 4 degrees Celsius water. Okay. So that is how now you have got a blanket of ice and you have relatively warmer water. So this enables a fish to be very, very happy in life. That's how marine life survives. Because this ice acts like an insulator. Ice is a very good insulator or bad conductor of heat. If you remember science class in your high school, in Alaska region, long time back, people used to construct their houses made of ice. That sounds very weird at the beginning. That, sir, outside it is very cold. So to protect me from the cold weather, I will definitely not be using ice. But the irony is, ice will protect you from extreme cold, not normal cold, extreme cold, because ice acts like a bad conductor of heat. Yes, 0 degrees Celsius is better than minus 40. So it is only okay when the temperatures are sub-zero. Don't think I will, sir, I will also put ice around my house, then my house how will be warm. No, no, no. Outside it is so cold that you start feeling 0 degrees Celsius or minus 1 degree Celsius is 100 times better. Okay, so that is in very, very cold regions. So that is exactly what happens. It acts like an insulator. This is warmer water and the fish survive. Now, it is actually funny thing to think about it, whether it is God or whether it is by chance that the life on earth requires water to survive. And it so happened that nature decided that only water is that one specific liquid which will show this anomalous behavior. And that too, it shows that anomalous behavior not at 20 degrees to 25 degrees Celsius, but exactly near the freezing point. So that this blanket of ice can be formed. And nature decided that ice is the one which will have bad conductor and it will not allow the cold to enter inside that warm water so that my dear fish and whales and sharks can survive. So it's very interesting to think about how nature would have designed it, or there is some bigger power like God who has designed all of this. Because it sometimes feels that it is not by chance, but maybe by purpose. Isn't it amazing? I hope I have answered your question, Shubhaya Kumar. Yeah, perfect. Let's go to some questions coming up on your screen. Here it is. A gun fires a lead bullet of temperature 300 Kelvin into a wooden block. The bullet, having a melting temperature of 600 Kelvin, penetrates into the block and melts down. If the total heat required for the process is 625 joules, the mass of the bullet is JEE Mains 2025. Options are 20, 15, 10, 5. I don't need the options. We have to just solve it. What will you do with the options? Nothing, right? So no point. So just solve it. Okay. So what will we do? What will we do? Yeah. Come on. Think. A gun fires a lead bullet. Temperature is given into a wooden block. The bullet has a melting temperature of 600, penetrates into the block and melts down. If the total heat required is 625, the mass of the bullet. I think they have not given some data like L or S or something. Maybe we'll see. If we require, we will just put it in variables. Maybe in the solution slide they have used it. In the question, it has not got printed over here. No issues. I'll just write it down. Now the bullet's temperature is 300 Kelvin. Now what happens is, once that bullet, which is at 300 Kelvin, enters that wooden block. Okay, this is that block. It enters into it, it has a melting temperature, and it is given that it melts down. Meaning, once that bullet enters, all that heat, which is of 625 joules, all that heat goes into number one, taking the bullet from 300 Kelvin to its melting point, because it won't melt at 300 Kelvin. So that heat will go in increasing the temperature from 300 to 600. Once it reaches the melting point, then that heat is also going into melting it. So that remaining heat goes into melting it into the liquid at 600 Kelvin. That is my fundamental understanding of the question. So therefore, I will then say that my heat is mass of the bullet into specific heat capacity into delta T, because that's the formula for heat when you change the temperature for a solid or a liquid or a gas. But once you change the phase, then the heat formula is M into L. Is that right? Great. So I just have to substitute the values, but before substituting, what is asked is the mass of the bullet. So if I take M common, I will have S delta T plus L over here. So that is basically Q. Therefore, my mass will be Q divided by S delta T plus L. How much is the heat? 6 to 5. How much is the S? Not given. I think that is what is missing. Delta T is given. 300 to 600. Obviously, that is 300 difference of temperature plus latent heat. That is not given. Okay. So, I think in the data part, it was missing. Like I can see, the value of S seems to be 125. The value of L seems to be 2.5 into 10 to the power 4. So that part was not printed over here. So I'm just writing it down for you. S is 125 and the latent heat supposed to be printed. Where is it? Is 2.5 10 to the power 4. 2.5 into 10 to the power 4. So just have to put that over here. 2.5 into 10 to the power 4. And what is this? 125. Solving this, you are going to get the answer of the mass as 1 by 100th of a kg. Basically 0.01 kilos, or basically 10 grams. So the mass of the bullet is 10 grams. That's it. Clear? So, sometimes you might have heard about ballistics investigation. So I know the bullet was fired at room temperature. Okay, so I know it was 300 Kelvin. And then I know the bullet was made of this material. Imagine you are Sherlock Holmes, and melting point, material is made of this thing, lead, and lead will melt at 600 Kelvin. Then I know how much heat was required. So from that, I can do the reverse calculation of how much mass of the bullet would be there. So that is a very interesting, investigation that we have just done. Very good. Awesome. Let's move. Let's move. Let's move. Let's move to the next question coming up on your screen. And here it is. This is also a very similar question. Water is falling from a height of 200 meters into a pool. Calculate the change in the temperature of the water, assuming no heat dissipation from the water into the pool. Take G as 10, specific heat capacity of water as 4200. Interesting. Let's understand what is really happening. You have water which is falling. So let's say this is the water which falls from a height of 200 meters. And once the water falls into a pool, the uh, rise in the temperature of the water, assuming no heat dissipation from the water into the pool. So this water which is there, which has fallen into that remaining water which was there into the pool, I have to find how much temperature has changed of that particular water. I also know how much mass. I do not know. Okay, I'll just assume it as M. So no heat is going from the water which fell into the remaining water. That is the meaning of it. Assuming no heat from the water into the pool. This is a water and this is the pool. Okay, so think of this remaining water as the pool. Okay, so all my gravitational potential energy will go in heating, and raising my temperature. Okay, gravitational potential energy is mgh. Heat required will be ms delta t. M will get cancelled. Yes, can you see that? This m and this m has got cancelled. Very good. So what do we do now? G is 10. H, oh, what is it? 200. Okay, so I'll put 200. S, where is S? Here. 4, 2, 0, 0. What is delta T? Oh, that only I have to find. No. So delta T over here. This 0, these two zeros went off group. So 10 is equal to 42 into delta T. So delta T is equal to 10 by 42. Do the math and tell me how much is it roughly coming out to be. It's like 1 by 4 approximately. So it will be close to 0.25, I'm guessing. Just check out. How much are you roughly getting out to be? Close to 1.25. Yeah, everyone, just check it out. But this is 10 by 42, 0.48. Oh, sorry, I missed one more 2 over here. Sorry, guys. See, that is what happens sometimes. This is 20. So sorry, guys. This 2 was there. I missed that. 20 is there. So this is 10 by 21. Sorry, 10 by 21. So this is like half. So it will be like 0.5, but slightly less than 0.5. So I will not even waste my time calculating it. Slightly less than 0.5 is 0.48. So I know the answer should be 0.48. Answer should be 0.48. That's it. So I'm just going to mark the answer as 0.48. That's it. That is the answer. Got it? Clear? Yeah, I had missed that too by mistake. Yeah, cool. Very good. Excellent. Amazing. Go. Let's go to the next question. Match the following. Match the following. What is it saying? Heat capacity and units, specific heat capacity and units, latent heat and units, thermal conductivity and units. Even if you don't know one or two of them, you can still solve it. Look at the options. A is going with 3, 4, 3, 2. Okay, B is going with 1, 3, 4, 3. C is going with 2, 2, 1, 1. D is going with 4, 1, 2, 4. So either solve for A and B together and that's it, your job is done. Heat capacity versus specific heat capacity. If you think about just specific heat capacity S, then I'm talking about specific heat capacity S. The unit is always heat, which is joules per mass, which is per kg per Kelvin. Heat energy per mass per Kelvin. So joules per kg per Kelvin, that I can see over here. So B should go with 3. 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 Okay. So automatically C and D are eliminated. Now look for A option, which is just heat capacity. That is how many joules are required per Kelvin. Just heat capacity is how many joules are required per Kelvin. So A is going with 2. A is going with 2. I don't even have to waste time checking for C and D. The correct option will be obviously D option. Got it? That is how smartly you should work in the real examination. But somebody might know thermal conductivity, they will solve it for that. If somebody knows latent heat, they will also solve for that. So latent heat, C option will be 1 joules per kg latent heat, guys. Yeah, this is latent heat will be joules per kg. L, because Q is M into L. So latent heat will be Q by M. Mass is there below, heat is there on the top. So joules per kilogram. So that's why the option is 1. Thermal conductivity is a part of heat transfer. 3 modes: conduction, convection, and radiation. So conduction part has the concept of thermal conductivity. Okay, so from there you can get it. Okay, perfect. Let's do one more question coming up on your screen, and here it is. During the melting of a slab of ice at 273 Kelvin, 0 Celsius, at atmospheric pressure, internal energy remains unchanged. Positive work is done by ice water system on the atmosphere. Positive work is done on the ice water system by the atmosphere. internal energy of the ice water system decreases. Interesting. Very, very nice theoretical concept, guys. Think about it. Think about it. Now, if you visualize, for ice, the molecules will be more structured, the bonds will be stronger, isn't it? That's how the molecules of ice will be bonded in case of ice. But in case of water, those molecules are slightly better in motion. They are moving slightly randomly here and there. So they are a little bit free. Yes, they have more energy in case of water. So clearly the internal energy will increase. So let's end the debate of internal energy. It says unchanged. This is obviously wrong. Internal energy of the system decreases. This is also wrong. So either it is B or it is C. Okay, perfect. Now, if you look at ice versus water, ice has a density of 900 kg per meter cube. Water has a slightly higher density. If it is higher density, that means ice occupies more volume. Ice will occupy more volume as compared to water. Water will occupy less volume because it is more dense. So in this process, volume has reduced from ice to water. If volume reduces, work done by water, work done by water from ice to water will be negative in physics, because work is always done by the system in physics. Work is P delta V. Okay. So if volume reduces, work done will be negative. So saying positive work is done by water, by the ice water system on atmosphere, this is definitely a wrong statement. So positive work is done on the ice water system. That is correct, because if water does negative work, if the ice water does negative work, the atmosphere has done positive work. Hence the only correct option, because if this is true, then the work done by the surrounding will be positive. Hence positive work is done on the, this word is important. So option C is the right answer. Got it? How to get it? Everything has been decoded, dissected for you, conceptually applying everything. Okay? Very good. Excellent. Let's go to the last part, which is calorimetry, which is about heat exchange, and it's a very simple thing. So now we learned about heat exchange, we learned about heat involved, whether it is phase change or just temperature increase, ms delta T or ml, and all the graphs, everything related to that. Now, imagine two objects of different temperature are in contact, the higher temperature and the lower temperature. The higher temperature will cool down, the lower temperature will heat up until both of them equalize their temperatures. That's when no heat transfer will occur. One is hot, one is cold. Heat will flow from hot to cold until both their temperatures equalize. If this is hot and this is cold, then heat will go from this body to this body until their temperatures equalize. So this is exactly the principle of calorimetry, which says that the hot body will lose heat and the cold body will gain heat, and the heat lost by the hot body is the heat gained by the cold body until their temperatures equalize. So when your system and surroundings or whatever inside your system, two things are exchanging heat, the heat lost by the hotter body is the heat gained by the cooler body until they reach an equilibrium basically. Now usually these things are performed inside a closed vessel, where it's like you have put two people to battle. It happens, right? Sometimes in your class, in your school, in your college, suddenly you make a gang and you close the doors and you put two enemies to fight inside a class. Have you seen such fights? You better not be involved in such fights. And then those two people who hate each other are fighting, and you're just enjoying it from the windows or peeping through the windows, something. So exactly same thing happens. A calorimeter is like a closed vessel which does not allow neither mass nor energy to go out or come in. So calorimeter is basically a device which blocks the mass or the energy exchange to happen from the surroundings. It is completely isolated. So whatever happens, the battles, they have to settle it for themselves. So one is hot, one is cold, they battle it out until they reach a equilibrium. And in that process, you will see the temperature will finally stop changing, because you will see there is a thermometer kept inside that, and the temperature will first fluctuate and then it will slowly settle down. It will reach an equilibrium. And once it reaches an equilibrium, you understood the battle is over. And then you see, oh, everything is silent now. Nobody is fighting. So that's when you say the heat which is lost by the hotter one is heat which is gained by the colder one until they reach the equilibrium phase. Is this understanding? Everyone clear? So, there could be multiple examples of this. Like, for example, water with ice. Okay, you mix water and ice. If water is, let's say, 20 degrees Celsius and the ice is 0 degrees Celsius, what do you think will happen? Yeah, the ice will slowly start melting. No, it's a warm water, so ice will start melting. And maybe sometime or later they will reach equilibrium. But imagine this, you have 0 degrees Celsius water and 0 degrees Celsius ice. What do you think you will get? Will the ice melt or will the water freeze? Will the ice melt or will the water freeze? Both their temperatures are same. Don't worry about their phases. Doesn't matter. Nothing will happen. This will still remain at 0 degrees Celsius. No heat exchange can happen. Neither the water freezes nor the ice melts, because temperatures are same. There is no battle to be fought. There is no heat exchange that will happen. Keep that in mind. Yeah, there is no change at all. Okay, so very, very interesting. There are a couple of questions which we can do about it. One such question is this one, where you have a juice whose specific heat capacity is 4 calories per gram per degree centigrade, and you take 20 grams of it, and maybe it is right now at some normal temperature of 20 degrees Celsius, and you take water whose specific heat capacity we all know is 1 calorie per gram per degree centigrade. You mix a lot of water, maybe you mixed 100 grams of water, and let's say the water right now is at 0 degrees Celsius. You are just taking it out from the freezer. Question is, what is the final temperature of the mixture? That's the question. What's the final temperature of the mixture? First of all, let me just see who is hot, who is cold here. The juice is hot, so it will lose heat, and the water is cold, so it will gain the heat. So the heat which is lost in the battle is the heat which is gained by the other one. The heat is lost by the juice and the heat is gained by the water. So this is my starting equation, governing equation, the principle of calorimetry. That's how it starts. Let's assume the final temperature to be X. So think about it like this. The juice has a temperature of 20. The water has a temperature of 0. The final temperature could be X. Okay. So this is losing, this is gaining. So over here, if you ask me, heat lost by the juice, I can use mass of the juice. Mass of the juice is how much? 20. Specific heat capacity of the juice, which is 4, into the difference of the temperature, the positive difference, which is obviously 20 minus x. Do you guys get it? Why it is 20 minus x, not x minus 20 or anything else, x plus 20 or 20 plus x. Yeah. Similarly, the heat gained by the water, again mass of the water, that's 100. Specific heat capacity 1. Difference of the temperature 0 minus x, 0 plus x plus 0, x minus 0. Difference, positive difference, is x minus 0, of course. Just take the positive difference on both the sides. Drawing the simple thing, flowchart, can also give you the answer very quickly. 20 into 4 is 80. So we'll have 80 multiplied by 20 minus x is equal to 100 into x minus 0, which is just 100 into x. 0, 0 cancels right over here, this 0 and this 0. In fact, 10 also cancels with 2 and 8 cancels with 2, becomes 4. Okay, perfect. So 4 into 20 is 80 minus 4x is equal to 5x, of course. So 4x plus 5x is 9x. So x is 80 divided by 9, which will be, because 81 divided by 9 will be 9. So it will be almost 8 point something. And some of you have already given the answer, 8.89, almost. Yes, it will be almost 8.9 degree Celsius. So you mix the cold water with the juice, which is warm. The final temperature of the mixture is 8.9 degrees Celsius. So these kind of questions also do come. Okay, keep this in mind. Great. Let's see one of the PYQs which has come in the previous year questions. There is a copper ball of mass 100 grams which is at some temperature. It is dropped into a copper calorimeter. That means inside the calorimeter there is a tub, beaker kind of thing, which is made of copper, whose mass is also 100 grams, filled with 170 grams of water at room temperature. Subsequently, the temperature of the system is found to be 75. T is how much? Given room temperature is 30 Celsius, specific heat capacity of water is also given. Okay. Now, there is a copper ball. Okay, let's visualize. Nothing else we can do over here. Just have to visualize. There is a copper ball. Okay. How much is the mass? Let me draw. This is copper, which is 100 grams. I don't know what the temperature is, but definitely it should be hot. That's what I'm guessing. That's why, finally it will come to 75 Celsius. Now there is water along with copper. So there is water over here and it is surrounded by copper. It's in that vessel and both of them together are at room temperature, which is given to be 30 Celsius. This is water plus copper. Okay, water plus copper, that is also given. Now, after you drop that ball, what happens is, interestingly, that ball is here and inside that vessel, water is surrounding it. Yeah, it exchanges heat after some time. You find the temperature to be 75 degree Celsius. Now, looking at these diagrams, we can mentally picturize who is losing, who is gaining in this battle. Okay. It's obvious that this copper ball was hot. It is losing the heat. This copper vessel and the water were cold. They are gaining the heat. Okay. So the equation should look probably like this. The heat which is lost by the copper ball will be equal to, there is copper here also, the heat which is gained by two people, the vessel, the copper is a copper calorimeter, so the vessel basically, and also some amount of heat is gained by the water inside that vessel. This is my first equation, the governing equation, right? By using principle of calorimetry. Always visualize first. Notice how I'm drawing it, because with words it is very confusing. You can make a lot of silly mistakes. You spend that extra 20-30 seconds in visualizing, meaning drawing. You cannot visualize by dreaming in the exam. Draw it and then you will understand who is the loser, who is the winner in that battle. Got it? Okay. Now we'll apply formula. Which formula? MS delta T. Okay. So M is 100. Specific heat capacity of copper is 0.1. Difference of the temperature. Think about it. Earlier the copper was at T. Finally it came to 75. So T should be higher because it is hot, right? Think of it like that. So if you compare the temperatures, this T, this 30 and 75. 75 will be somewhere in between T and 30. So that is the reason why I should put this as T minus 75 is equal to this vessel. How much was that vessel? The vessel was also 100 grams. Copper specific heat capacity is 0.1. Change in temperature. The vessel was at 30, it went to 75. So it will be 75 minus 30. And in the end, for water, when I write it, 170 grams of water, specific heat capacity 1, the temperature of water was 30. Mixture temperature is already given. It is 75. So it will be 75 minus 30. In this entire equation, there is only one thing which I do not know, and that is T. Everything else is known. Solving it, you should get the answer, which comes out as 885 degrees Celsius. You solve this, you get it as 885 degree Celsius, which is option A, of course. Okay, that's it. Is that clear, guys? How to solve these kind of questions? Yeah, very good. So now in today's lecture, really you have gained lot of concepts, guys. This is insane what this lecture was doing for you. Okay, you have learned about heat, thermodynamics, zeroth law. What is heat? What is temperature? The temperature scales, their convergence, then expansion, apparent expansion, density calculations. Also, we have talked about how aquatic animals are staying alive, anomalous behavior, latent heat, phase transformations, also specific molar heat, all these concepts, and finally the principle of calorimetry. This big unit of heat and temperature is done. Okay, so I hope you enjoyed the class, because already kids are enjoying not just the classes over here, but also my Sigma classes, and I'm really proud about this. I'm really happy about this, and you guys are loving every single lecture, whether it is our YouTube class or whether it is my Sigma batch for JEE 2026. So keep learning, keep improving, keep practicing. Your Capto is there for you always. Thank you so much. Have a great night, but don't sleep. Practice, learn, revise. Maybe you have to do something. You might be feeling a little bit sleepy, but do not forget your goal. Your goal is to enter IIT. Your goal is to crack not just mains, but advanced. People who are going to sleep probably are going to lose out on some marks. You have that edge now. If you stay awake and practice 10 problems, you are better than maybe some 100, 500 students around you. Every day you practice, you do something which others are not doing, you are moving ahead by 500 ranks. Last 60, 70, 80 days, you decide how many ranks you want to go ahead by. Actually, as you go ahead and ahead, you will be taking leaps and leaps of jumps, because your momentum is going to build up, whereas others are going to lose focus. So you do not give up, my dear warriors. Thank you so much. This was your Captain Shreyas. Bye bye. Take care.